YouTube should pick it up. There we go. But it's black at the moment because there's no call.
Okay, let me do one then by myself. So. Okay.
No, hold on. I'm not done yet.
Okay.
If you had two scenes to be safe.
Yeah.
So this one you do add. Again, these will be saved. Do a window capture. Do changes to Windows 10, and then the Zoom meeting. Then that will save what was on the Zoom screen. You might have to resize it. So if we go full screen on here.
Can you let me enter that Zoom call?
Good morning, good morning,
Hello.
good people.
I've added Tress lecture theatre in. Is that
Yeah.
How is it going? Alright,
So
morning.
main is done. Joe has set the
Main
Tress.
is still showing 4-key on its...
Yeah, but if they change that, the slide, that will show.
yeah, but someone should be showing pets there.
Yeah.
Okay.
They should change that side on the thing.
Do you want to make me host?
Yeah.
And then we're done here. Well, I'm done here, and I can go and set up then back the
So
Bantam one.
that's you, yeah.
Yeah. So we just go to participants
You
and
Right.
make host.
Okay.
So I need to sign in a refrain and a Tress lecture theatre next door. Well, Bantam lecture theatre next door.
Yeah.
Yeah, I'll go and set the Bantam up
Yeah.
by myself.
So your window capture, you might have to resize it, but it looks okay at the moment. And then this one, just do a desktop capture as a backup.
Fucking horrible.
Display capture.
While cap.
Death.
Good morning, Robert.
Actually, this
Hello.
is scaring everyone.
How are you?
Do it,
I'm
that's the
very well.
default
Are
one.
you feeling okay?
But while
I'm
capturing this.
always filled with joy.
Just
How
as a
are you?
backup, so we need it.
Well, same as
97%. Depends on the size of the model. At the same time, fewer cipher operations also means less memory. So PrePDN also reduces the memory consumption by more than 97%. Here is the conclusion of our work. We present the first practical framework that can execute DNA inference while keeping both data and model private. We propose 4 algorithms to identify the core neurons and demonstrate the effectiveness of our prediction using 5 popular datasets and 4 models. We achieved up to 30 times speed up in homomorphic incubation model inference and reduced memory requirements by 97%. We would like to thank our sponsors. We also like to thank the anonymous reviewers and the shepherds for their valuable comments. Thanks for listening. I'm happy to take any questions.
Okay, let's thank our speaker. And same question, do we have, we do have the speaker available? Maybe?
Yeah, I'm here to answer questions. Can you hear me?
I'll give it maybe a minute.
I'm here to answer questions. Can you hear me?
I think so too. Oh, okay.
Hi.
Okay, we have Emily, the first speaker. Okay, great. Hey, Emily, can you hear us?
Yes, can you hear me? Can you hear me? I think there's something wrong with the Zoom.
Just a second.
Okay.
Here.
Again, Emily, can you hear us?
I can hear you. Can you hear me?
Great, yes, we can. Awesome.
Yay.
Yes.
I'm so sorry. I just received the correct link, so that's why I'm super late. I really apologize.
No, it's okay. We were figuring things out here too. Were there any questions for Emily from the first talk we had today? Yeah.
Hello, Sebastian Hasler from the University of Stuttgart. It seems that you assumed that your model training has Alice as a class. How realistic would that be in practice? I mean, if Alice is a class, then it's quite obvious that Alice's data would also be in the training data set, because otherwise it wouldn't make sense to have her as a class, right?
Yeah, so the facial recognition example is perhaps a little misleading. We hope that the context would be slightly broader than that, and perhaps Alice posts a specific category of images on social media or Visco or Flickr or wherever that could occupy a class in like an object recognition scenario, but wouldn't necessarily be obvious that it was her data. So facial recognition, yes, this is a super obvious choice. But if, for example, Alice had a hobby of flower picture taking or other sorts of image posting, then perhaps that assumption makes more sense.
Hello. Yes. Thank you for the presentation. This is Barry Merck. I live in Belgium. Probably also a clarification question. Could you please clarify why we need including isotopes in contrast to using membership inference types of scenarios where we can see for each given sample whether or not it was used in training without any isotopes included. So I kind of missed that.
Yeah, I mean, a membership inference is another option. However, membership inference is not necessarily always reliable. And so isotopes provide a stronger probabilistic signal that would ensure that the data use is detected. I don't believe it's always the case that membership inference will just work, particularly for more common elements of the training data set.
Thank you. Is that something that you also practically checked? in comparison?
It's been a hot second. I don't believe I did extensive experiments on that, but I believe there are several papers covering that kind of behavior around membership inference.
We have time for one more before we should move to the next speaker.
Hi, this is Chad Bowman from the Naval Postgraduate School. There were a couple of things I missed, I think, during the presentation, so these are more just elaborating questions. But regarding your heat map, what statistic did you use to quantify like your 1.0 results? Like, was this just a change in probability, or was this a definite shift in class, et cetera?
Yes, I did sweep a lot of details under the rug about that. So thanks for catching that. So that heat map is composed of results from a verifier procedure that's described in the paper. At a super high level, the verifier takes in two marks, one that is the correct isotope mark, and then, well, I guess it's two sets of marks, one that is a correct isotope mark, and then one that is a set of incorrect marks, tests them against the model, and then reports like a t-test result in whether the real isotope mark induces a statistically significant stronger shift in the class probability for the marked class than the fake marks. So the 1.0 is the result of this long chain of statistical tests, and it's giving like the average true positive rate of the t-test.
Okay, thank you. And then one follow-up on that heat map was, how were you quantifying visibility? Yeah, I think it went all the way down to 0.01 and then up. Was this just like a simple opacity setting in Windows Paint or something more complicated?
Yeah, when we blend the isotope into the image, there's like a little equation in the paper, but it's basically like 1 minus alpha is the visibility of the image, and then alpha is the visibility of the isotope. So yeah, you could think of it as an opacity setting of how strongly visible is the isotope.
Great, thank you very much. Look forward to digging into the paper.
Thank you.
Okay, thanks, Emily. And now we will move to our next speakers, Mindugas and Tanvir. Please, let's...
Excuse me, I'm here to answer questions for paper 2, if there's any.
Okay. Yes,
sorry to interrupt.
So before we get started, if that's okay, we'll have questions for the second speaker, if there are any. Sure.
Thank you for the presentation. This is a very general question. You seem to have very positive outcome for PREP-DNN. So I was just wondering, do you believe your solution solves the problem for the domain? Or do you think there is still something that we can do where this approach doesn't work?
Very good question. Although we have improved the performance by like 10 times or even close to 100 times, I think it's still, from real practical perspective, I think it has to be further improved before it could be really adopted in real world applications. The advantage of private DNN is that no matter how fast or slow you go with a fully homomorphic encryption, we can improve on top of that. So we do hope that fully homomorphic encryption could be more practical. Yeah, that's my answer.
Okay, thanks. I have a question for you too. So I was wondering, when you were identifying core neurons in your networks, it looks like you were using average case classification performance. But there might be some examples which are sensitive that might depend specifically on some neurons. And I was wondering if you considered any kind of like worst case analyses when you were identifying core neurons, or ways to identify neurons that were responsible for like particular examples, especially if those are sensitive.
Okay. Are you talking about the samples or the neurons?
The neurons with respect to maybe particular samples that are...
Oh, okay. We did not try that. Yes, we tested the average. So my answer is, on average, we are at the same performance with the original model. That means there could be some samples that are incorrectly classified with a core neuron selection, but there are maybe compensated by some other samples which were incorrectly classified, but now they are correctly classified. We only look at the average case, not the specific samples.
Okay, thanks. And we have time for maybe one more question if there is one. Okay, if not, thank you very much again. And yes, please.
So, hello everyone. Today we'll be presenting our paper Wildest Dreams, Reproducible Research in Privacy-Preserving Neural Network Training. So, in this presentation, we'll kind of go through our motivations and talk about privacy-preserving techniques that exist. And specifically, we'll talk about homomorphic encryption and secure multi-party computation in neural network training. So, initially, we set out with a goal of testing out various privacy-preserving techniques, and we ended up identifying cryptographic methods that exist, data modification, distributed approaches, and hybrid approaches that exist. And more specifically, we ended up deciding on analyzing homomorphic encryption and secure multi-party computation. However, as we started looking into these papers, we started noticing a bit of a bigger issue when it comes to analyzing them, and that was that most of the papers that we found did not particularly support open science and made reproducing the results quite difficult. But we'll get to that a bit later. First, let's talk about some preliminaries. So, in a usual homomorphic encryption situation, we might have a user and a cloud service provider. The user wants to outsource some data and gain some insights on it. So he would generate some keys, use the public key to encrypt their data and outsource it to the cloud service provider. Then the cloud service provider can use the evaluation key to compute some sort of arbitrary function. Let's imagine a machine learning model in this case, and then send those encrypted insights back to the user who can decrypt it with the secret key. And homomorphic encryption can be classified into partially, somewhat, leveled, and fully homomorphic encryption, where the main differences between them is the types of operations that can be done and the amount of times that they can be done, as can be seen here. And there are also a variety of schemes that exist to basically enable homomorphic encryption, ranging from the original RSA to more modern ones like BFV, BGB, CKKS, and TFHE. And these latter four were the core focus on the HE parts here, namely because of their prevalence in machine learning and machine learning training. All of them have their own advantages and disadvantages. And yeah, as we identified these schemes, we ended up searching for papers that exist within this domain. And we ended up identifying 8 machine learning training papers that use homomorphic encryption. You can see them here, and the few that I want to specifically mention is Glyph, because it uses cipher switching, where most of the operations are done through BGB, and then nonlinear activation functions such as ReLU are done with TFHE and the fast bootstrapping that it provides. And then also there's Poseidon, which does a similar thing. However, it uses specifically secure multi-party computation to become a multi-party homomorphic encryption technique. So, as mentioned, most of these solutions have their own supported machine learning layers. All of them provide nonlinear activation functions such as ReLU or softmax, usually through polynomial approximation, or in the case of TFHE, that is done through binary lookup tables. And then, depending on the research goals, there was also implementations of convolution and max pooling or average pooling layers. However, as I hinted at the start, the main thing we wanted to talk to kind of like look into is the overall reproducibility of these papers. And we noticed that none of the papers provided, despite being published in top venues, had any sort of open source implementation. They did provide some sort of algorithms to help re-implement these results. However, this is a bit of a double-edged sword, namely because all of these works are done in different libraries or even different versions of the same library, creating a bit of a discrepancy when trying to re-implement the results and reproduce the results of the paper. Namely, HElib hasn't been updated in over a year now and has been replaced by OpenFHE, which is quite structurally different. And Microsoft Seal has also been been quite extensively updated and does not work the same way. Libraries such as Latigo are made in Golang, while all the others are made in C++, which also creates more problems than solutions on how to actually reproduce everything. So from this, we kind of got some takeaways that overall PPML training has made a quite giant leap in improving both training time and the accuracy from the first works from Nanda Kumar et al. However, we found out that reproducibility in HE PPML research is extremely lacking right now, with nobody providing artifacts or open source implementations. And also, there are a variety of libraries that exist for implementing HE. New ones keep popping up, like Concrete or the OpenFHE library, while others tend to be abandoned or completely revamped. So I pass it over to my colleague Tanvir to present our findings also on secure multi-party computation.
Thank you, Mindagos, for the first part. So as mentioned by Mindagos in the beginning of the presentation, that in this work, we analyzed two privacy-preserving techniques. The first one was the HE, which Mindagos talked about. The second one is the secure multi-party computation. So in general, about secure multi-party computation, so we have multiple parties. Both these parties do not trust each other. Party A do not trust party B, and similarly, party B do not trust party A. But they achieve the same goal. And the goal is to analyze the data without revealing any sensitive data. So one solution is to use the trusted third party, but it is about secure party computation. So this is the taxonomy of the SMPC. So these are the papers that we have covered for the SMPC. So in total, we have considered 17 papers, as can be seen in the figure. So in this we cover what type of threat model they have used, what are the number of parties that they considered, and what type of platform, either CPU or GPU, they have used. So on the left side, they use these as a base paper, while on the right side, this is the new iteration of the paper. So they used, like for example, the secure NN, they use secure ML as the base paper, and the same apply for the rest of the figure. So the key consideration that we consider for this SMPC are the first one is the functionality. What do we want to compute? The other one is the security type. I will talk about it in the next slide. What type of threat model that they have, or what do we want to protect against, and what type of network model is used. So the key consideration. So over here, as can be seen, the first one is the privacy. So in privacy, no user learn more than what is prescribed output. In other words, what can be learned from the output can be revealed about the user input. So in this one, we can see that most of the so in this one, as can be seen, that most of these, they provide the input privacy, while only the area and which use the FSS, they provide the also the model privacy. Other than that, in my previous slide, I mentioned that I'll be talking about the security. So this is the first one is the guaranteed output delivery. So as highlighted in the figure, so these was provide the guaranteed output delivery. The second one is the fairness, which is a weaker assumption. So these are the papers that also provide the fairness, and the third one is the board, which is weakest assumption, security assumption, and these are the papers that are highlighted that provide the security assumption. The next one is the in my previous slide I also talked about the threat model. So as can be seen, almost all the papers they consider the semi-honest threat model, but some of them they also consider the malicious, both the models, the semi-honest and the malicious threat model. So they also supported most of the machine learning layers like the convolution, ReLU, max pooling, and linear layer. Other than that, the SMPC technique that they have used is the oblivious transfer, garbage circuit, secret sharing, and the new technique proposed by Elite Boyle, which is the function secret sharing. And also at the end, they also considered some of the what they considered local area network, while the others they consider both like local area network and the wide area network. So what are the takeaways? So initially, we plan to cover the initially we plan to cover most of the set of the artwork in the privacy preserving machine learning by considering the techniques HE and SMPC. For this, we collect 25 set of the artworks. So we successfully reproduced the result for 4 techniques. As Mindagos mentioned in his part, that none of the HE papers they provide the open source implementation. However, in the SMPC, some of the work they provide the open source implementation. So we reproduced the result for 4 SMPC techniques, but unfortunately, we were unable to reproduce the rest of the 21 techniques. And the reason for this unsuccess is first of all, these do not provide the open source implementation of their work. If they do provide the open source implementation, they lack the proper documentation. Other than that, it is very difficult to implement those techniques because they use some platform. They differ also in SMPC. There are the number of parties vary, so it's a bit difficult to compare. And there are some other difficulties, as Douglas mentioned in the beginning, that there are some library issues, hardware issues, etc. So conclusion and future was, so from this SOK, we conclude that in general, HE techniques, they are computationally expensive. But while the SMPC techniques, they require very high communication cost. So the biggest issue that we realized in this one was the reproducibility, as also mentioned by Douglas, very few provide open source implementation. So in order to address this type of issue, the first thing that we should consider is the whole community. They should, it is a community-driven approach. So all of us should consider this thing. So authors on their side, they should provide the open source implementation of their work. And also the conferences and the top venues, they should encourage the authors to submit the papers along with the artifacts. So this is the whole from our side. If you have any questions, so please feel free to ask.
Thanks so much, Mendugas. And we have time for questions.
Thanks. I'm not sure if this is a question for you guys, but so homomorphic encryption and secure multi-party computation, why would one use one over the other if they're tackling the same problem?
Yeah, in a sense that why someone will use HE in comparison to SMPC?
Yeah.
Okay. So it depends. Like, for example, in Mindaugas, in his slide, he considered the scenario as machine learning as a service. So the cloud service, the cloud server provider, they train the whole model, right? While in the other case, we have like the other scenario in which there are multiple parties involved. For example, a research institution or research institution in a hospital, they want to collaborate, but they do not want to share their data. So if you want to outsource your, if you want to outsource the model, then it's the other, the scenario of machine learning as a service. But on the other case, it's a joint work.
Okay. So in the first case, you also want to say hide the model as well.
Yes, in the privacy preserving training. Yes, exactly.
Yeah. Okay, thanks.
Okay, we have time for more questions. I'll ask one. So what do you think are some of the reasons why researchers aren't making good artifacts of their work right now? Is it really hard to like follow good practices and make a Docker instance with some of the libraries and APIs that are available? Or is it just laziness? Is there some other reason, maybe not being required?
Overall, there are a variety of reasons, and it very much depends from in a case-to-case basis. But some people might not want to share it because it's intellectual property. So let's say if they're working with Microsoft or some sort of company, they might not want to share the inner details and make it reproducible. But in other cases, yeah, it might be just difficulties, so to say, implementing everything and making it fully documented. And in some cases, it might have other reasons that very much depend on researchers.
Okay. Are there certain like platforms or languages you've noticed? Like I know you said there was one system that was based on Go, but the rest were C++. Are some of these like ecosystems a little easier to reproduce than others, or is it like everything C++ and everything is kind of dependency? There are issues with getting things to be reproducible.
At least in the case of Seal and various like HE libraries, there can be some difficulties fully setting everything up. Some libraries are only available on Linux, others are only available, like, are more preferred to be on Windows systems, and this creates maybe you don't have the hardware to properly implement everything, or maybe the libraries are just outdated and do not install properly.
Okay, and is it the same case for the SMC? Yeah. Great. And we we have time for maybe one more question. Yeah.
Hi, thanks for the presentation. I'm kind of following on his question. What do you think are maybe some of the incentives that would get some of these researchers to start open sourcing some of their work, especially if you are talking about a lot of them are working alongside commercial partners, sometimes Microsoft or other ones, as they actually do their research to start?
Overall, it's a very interesting question, and that's kind of a thing that has to be discussed in the wider research community. I feel like one of the main motivations is trying to advance the field as it is. So wanting to properly advance the field, we have to allow them for results to be comparable, that we could reproduce the results, kind of help out with, help iterate on existing works, and also, well, provide new solutions. So I feel like it's more like a thing about just as a community coming together and kind of like encouraging that despite, let's say, commercial ties. But it very much depends. Maybe there should be some sort of encouragement, either from venues or something like that.
Okay. Thank you again, Tandra and Mendua. And our next speaker is Ishan Wu, who is with CISPA, a second-year PhD student.
Hello everyone, I'm Ishan Wu from CISPA, and today I'm going to present our paper, Link Stealing Attacks Against Inductive Graph Neural Networks. And this is a joint work from with researchers from CISPA, Hong Kong University of Science and Technology, University of Birmingham, University of Lausanne, and Duke University. And let's get started. And nowadays, machine learning models are playing crucial roles in our daily life. One of the key factors for them being so successful is the data. Only with a huge amount of data, it can power tons of real-world applications for us to use. And among of these data, there are a special type of the data that comes naturally in the format of graph. The graph data basically contains the nodes and edges that connect these nodes, and making it different from those data that is independent of each other, like the image data. And to take full advantage of this graph data, researchers create a special type of neural network called graph neural networks. The core idea of the graph neural network is to leverage the neighbor information observed among nodes to learn embeddings to perform the downstream task. Here in the paper, we talk about the node classification task. Here, the graph neural networks learn the node embeddings to predict the labels of the given nodes. And we can implement the graph neural networks in two ways, transactive and inductive. Let's first talk about the transactive setting. And in this settings, the entire graph, include the node attributes and edges, can be observed during the training by the transactive GNNs, and only the labels of the test nodes are unknown. And during the inference, user only needs to feed the identifiers of these unlabeled scene nodes into graph neural networks and obtain the prediction results. And these transactive GNNs cannot be generalized to any new nodes, new graphs. They can only predict the label of scene nodes during the training. However, in reality, there are many real-world applications where the graph is actually evolving. So here comes another setting called inductive settings. During the training, only the training graph can be observed by the inductive GNNs. And during the inference, the users need to construct their own subgraphs, either zero hop, which has almost no neighbor information, or several hops that there can include some levels of neighbor informations. Here we only consider 1 or 2 hop, which is very common in evaluations, and to obtain the predictions of these unseen test nodes. And from the above, we can see that there are differences from these two settings. The transactive GNNs are actually memorize the training graph and generate fixed embeddings for each node in the graph. And compared to this one, the inductive settings learns to generalize these node embeddings functions, which can apply to other new nodes, new graphs. So in this way, we can see the inductive graph neural networks are actually more generalizable and flexible for these dynamic real-world applications, especially like the social networks and recommendation systems, which are adding or deleting nodes and edges from time to time. And due to the prevalence of graph structure data, there exists some previous work shows that the privacy issue of this data in graph neural networks. And there is one previous work shows that the transactive GNN actually leaks the graph information, making it vulnerable to the link stealing attacks. What's the link stealing attack focuses is actually a research question. It's like given two nodes used to train these black box graph neural networks. Can we predict whether these two nodes are linked or not? Why this attack considers a privacy issues? In one case, social relationships, which are normally encoded by edges in the graph, often represent privacy-sensitive information among these social network users. So it actually naturally makes us wondering, what about the inductive graph neural networks, as it actually has a wider application in the real world, and the privacy issue in these inductive GNNs is necessary to be explored. But what are the challenges for us to apply these link stealing attacks against inductive graph neural networks? Let's first see the transactive graph neural networks. It's like memorizing this training graph and generates a fixed embeddings for these scene nodes. But for the inductive graph neural networks, we are learning some generalizable embedding functions, general embeddings based on the given subgraph, the one user needs to construct. So in inductive graph neural networks might not be that much vulnerable to these link stealing attacks because they are not learning some specific information of the training graph. And another challenge is that the adversary needs to construct their own subgraph as a query to the inductive GNNs. So which actually means that the adversary can only rely on some limited information, because the most important thing is here the neighbor information for the link they want to intend is always missing. So the subgraph information is always incomplete. And for the transactive GNNs, we notice that the adversary only queries with the identifiers and to get the fixed embeddings and learn during the training. So it means that they're actually using the full neighbor information to generate these node embeddings. While for the inductive GNNs, the adversary actually queries with their own constructed graph. It depends on how much knowledge they can have for the training graph and obtain the node embeddings based on these subgraphs. Now let's look at our threat models. The adversary can construct the graph, subgraph based on their own knowledge, either zero hop with no neighbor information at all, or 1 or 2 hop with limited neighbor informations. And having these subgraphs, the adversary can choose to have or not having these 3 types of features, node features and posterior features from the inductive GNNs, and some traditional graph feature like the common neighbors. And from these results, we can see that the proposed link stealing attacks actually performs very good in all cases, like most of them are surpassing 80%. And especially for the cases where no neighbor information is provided, it can achieve a good result. And meanwhile, from the left to right, we can see here the adversary leverages more information to enable the link stealing attacks. And indeed, more information from left to right, it can achieve a better performance. And as the final conclusions, we propose in total 10 link stealing attacks against these inductive graph neural networks. And from the previous table results, we can see that there is no neighbor informations. Even if there is no graph neighbor informations, our attack still achieves a very good performance. And with more information, like combining the node features or traditional graph features to enable our link stealing attacks, it can indeed achieve a better performance. And finally, in our paper, there are also some other experiments shows that the higher robustness of our attacks and better performance than some traditional link prediction methods, and showing that these inductive graph neural networks actually indeed leak privacy informations. And if you do want to know more detailed evaluation results, check out our papers. And that's it for the presentation. I'm happy to take your question.
Thank you. Yes, if there are questions in the audience, and I can start with one for you. So for some of the data sets you considered, could you just talk through maybe what an attack would look like if it was being implemented, like how the queries are being made, and maybe like who's holding the model in those cases? I was interested in like the PubMed data set, for instance. Like, could you speak a little more about how, like, give an example maybe of what would be learned in that case and who would be holding onto the model that the adversary is querying?
The adversary will first like train a shadow model, which like mimics the behavior of the target model, and then they should have first the two nodes with the node attributes, like as a basic informations. And if they do not have any graph information, like what I say here, zero hop, they need to like build a self loop edges. So these two nodes can be considered as a subgraph to fit into the graph neural networks and obtain the posteriors. It's like the prediction results from the graph neural networks. And with this information, just the posteriors, we can infer whether these two edges are linked or not. And for the PubMed cases, here we can see the A0 is actually the results for the zero hop, like no graph informations, and it achieves a pretty good, I would say.
Okay, great, thanks. And I'm wondering, did you consider defenses in this work? So you showed a lot.
Sure.
Oh, yeah.
Yes, we do have two defenses, like some state-of-the-art defenses for these graph networks, like differential privacy. And we found that if we only have a like tiny, if we want to achieve a good defense performance, we need to have a very high privacy budget. So it consider not it cannot work in practice.
Okay.
Yes.
Okay. Any other questions in the audience?
Thank you for the presentation. I'm Son from Arizona State University, and I want to ask you to elaborate further on what kind of information does the attacker have? Does he have the information about the training graph, or he just have the graph node that he wants to query?
It just has a graph nodes. And if we actually consider three more scenarios. First, you need to have the node attributes. That's like must-have information. And then you can, based on your own knowledge, to build the subgraphs. If no subgraph information, then zero hop. If you have some limited information like one hop, you can add it on your own, build your own subgraphs, and fit to the graph neural networks. It's like basically it depends on how much you have. You can add it all on your subgraphs and do the query.
So the node in the subgraph doesn't need to be coming from the training data. Right?
If you want to infer if there is a edge in the training graph, the first thing is you need to know the training nodes. Then you can consider if they have the connection edges.
Thank you.
Yeah.
And any other questions for Ishan? Okay, thank you very much, Ishan. And we will move to our fifth talk, which is another recorded talk.
Hello everyone, I'm Shirley Wong, a PhD student from Stevens Institute of Technology in Jersey, US. Today I'm going to present our work titled Structure Membership Inference Attacks Against Graph Neural Networks. This is a joint work with my advisor Huang from Stevens, and this work is funded by National Science Foundation. Graph neural networks are vulnerable to various types of attacks, such as membership inference attack, attribute inference attack, property inference attack, structure reconstruction, and so on. Because there are a bunch of words for some privacy attacks against GNs, I only cite some typical words here. In our work, we focus on structure membership inference attacks, abbreviated as SDA. The test goal is to infer if a set of k-target nodes forms a specific structure in the training graph of a given GNN, and now the previous work have studied SDA. The reason why SDA is important is that it can pose significant privacy risks to individuals, for example, the secret romantic relationship among the users. In our work, we focus on two fundamental subgraph structures. The key-hop parse denotes the sequential of k-adjacent edges connecting distinct nodes. In the paper, we only consider loop-free key-hop parse, and the clicks represents a subgraph comprising k nodes where each node is interconnected with each other nodes. For example, in the figure, the node BDE form a two-hop parse and node ABC form a straight click. Straight click is also referred to as a triangle. We make the following contributions. First, we formally define the key SDA problem. Then we devise the black box attacks that infer structure membership using predicted outputs runtime model. We extend the black box SDA to white box, which leverage the embeddings for attack inference, and we extend SDA to SCA that infer specific subgraph structure of the target nodes. We evaluate the performance of SMIA on three representative GM models and real-world data. After that, we design defense mechanisms that have purpose noise to the embedding dimensions of least that leaves significance. And empirical assessment demonstrates that our defense achieves the better defense utility trade-off than the distinct defense mechanisms. As I introduce the paper for the following four aspects: the design of the attack, the evaluation, the defense mechanism, and the conclusion. In this work, we assume that the adversary have a black box asymmetric type model, namely the posterior classification probabilities of specific nodes by creating the target model and the shadow model. And here we also have a shadow model, which may have its own structure, its node attributes, and may for different domains of the time graph. Then the SMIR is denoted as the mapping function, given the posteriors VI to VK from time model and the adversary knowledge. The adversary can map them to different classes, whether they constitute a k-click, k-1 hop pass, or the absence of both structures. And I'll introduce the attack. It includes three phases: the shared multi-chain base, attack multi-chain base, and membership inference base. In shadow marching phase, the raster randomly unsample T subgraphs from the shadow graph G shadow to train the T shadow model. In attack marching phase, with the posteriors of nodes from shadow graph for shadow model, we generate a smear, train dataset, and train the attack classifier. In the feature design, for each node set and each similarity magic, we pairwise calculate similarity within a node set, and next sort the similarity in descending order, then concatenate the rank similarity based on all types of similarity matrices to form the attack feature. And then add the pair of attack feature and its corresponding label to the attack training dataset. In the membership interface, given node set and posteriors of nodes, the DAG generates a tag feature by using the same width as that is using the attachment training phase, which is the input of the training classifier to produce a label of the tag model set. Let's now introduce the variation part. We consider three real-world data sets, namely SciSeer, Google+, and LaSci, which are popularly used for graph learning in the literature. We consider three widely used GM models, namely GCN, SAGE, and GAT. We use attack accuracy, the AUC true positive rate at first positive rate to measure the attack effectiveness, and use the AUC of the classification to measure the time model performance. We compare our attack model with the three baselines in three data. Baseline one is threshold-based method, which is ensemble of three threshold sub-attacks, and each sub-attacks use one of the similarity matrix. In baseline 2, we use the combination of posterior vectors instead of the combination of similarities. And in baseline 3, we adapt the existing posterior base LMIA to our setting. Then we improve all the links based on LMIA first and then for the subgraph. We evaluate the effectiveness of SMIA and tree settings, one of the non-transfer setting, namely the shadow dataset and type dataset are sampled from the same graph, and the tidy GN and the shadow GN with the same attacher. Another one is the transfer setting, namely the dataset transfer setting, and the GN model transfer setting I will introduce later. This figure shows the attack performance and the non-transfer setting. The 3S MIA engine for 3 clicks and 2 hop paths and 9 of them, and 4S MIA engine for the 4 clicks and 3 hop paths and 9 of them. This figure will observe that the attack accuracy of the attack is highly effective, and our attack outperforms all 4 baseline in all settings. The figure shows the attack performance and the transfer setting and non-transfer setting. The dataset transfer setting, the shadow dataset, and type dataset are sampled from different graphs. And in the GN model transfer setting, the shadow GN and type GNs are different with different attachers. For both settings, we observe that the attack remains successful at both of settings.
I've just gone to tell them to not do it this last sheet, so yeah. All right, well, I'll Google that fast and figure out what it is.
Number 6 SMIA and 10.
Why do we give people right access to the registration sheet?
Because they need to know if someone's going to the hike or someone's like, so if you show up and you say, I registered, so it's like, would you want to go to the gala dinner, go to the hike, if you've registered for those things.
So if you notice.
For setting, the results show that
Anthony is messing with the registration sheet.
Yeah, he's doing it by accident. Like he's not doing it deliberately, obviously. It's like I'm not suggesting that you and I are chatting.
No,
but it's like it's the trick in Logan is earlier, and like it was painful. It was like having my grandmother do it.
Okay, well maybe then he should assign this responsibility.
That's what I'm going to suggest to you.
So don't suggest it to me.
And as I introduce our defense mechanisms.
Okay, because
I know you're not in my management.
To analyze to the values
but I can say to people, no, but I think you should raise it with Sophie. You know, that gently and politely take him off.
Yeah.
I think you should tell them.
Yeah, that's fine. I mean, you say you're not in my management. You're an influential chap. Notice I didn't say fellow, because Becky's boss is a fellow.
Fellow of what?
Royal Society of Chemistry. He runs a 5K faster than you.
short value-based model of method. Second, we rank
Because I told you how fast I run
the
5K. You're very stupid about what.
Third, we add up the norms in the partial value dimension of
Brenda is older than you.
lowest importance.
Brenda is older than you.
The red dimension and
In about 23 minutes? That's it.
Compare with the best
Well, yeah,
mechanism
well,
with
it's
two
just
besides the
part of
differential
Becky's job is
probability-based method
Brenda
and multiple
specified that
method.
his technician, because
The
they were his
differential
technician.
probability-based method
It wasn't because when the role was being filled, they must have their own office. They have their own office. And he insisted that in order to get a person of requisite quality, they must be paid this. He's not in our management team.
Against
He's John.
SME or GS with various noise scale and preparation ratio and evaluate the accuracy and time model
I think people say no to Brenda and he stomps his foot.
different settings. Then we plot the trade-off curve. Each point
Brenda's a very
corresponds
nice
to a direct pair of the attack accuracy and time model accuracy.
People talk
Star means attack accuracy and
it's
time
like,
model
and your other one is
without
this is
defense.
basic stuff.
We preserve data with the consistent data from both baselines, considering the trade-off
Yeah, it's just
when the attack accuracy approaches the time model performance while methods to the high.
Step off the spreadsheet is the
Just
point.
summarizing
So
the work we designed for structural membership in this attack against GNs and our improved study demonstrates the effectiveness of SMIA against string represented GN models. We designed a new defense mechanism to counterbalance the GNs
there is an issue, you just get like the Sophie.
and showcase that our defense approach
again,
provides strong defense
it's just about skill sets.
SMIA while maintaining tight model accuracy through evaluation.
I mean, I haven't been on the diplomacy course that you suggested that I've been. I'm just a naturally empathetic fellow.
Across diverse adversary setting, and we always tend to scope as mere
Signals, yeah.
the other.
Wow, yeah, that's maybe when you're a technician, getting them more offices.
Strongly connected components and stars. Okay, this is the end of my talk.
You may.
It's
just me here.
I'm happy to take questions.
No, I
Thanks, Julie.
Because this will come back to bite. But I remember that I was having this conversation in my former university with my dean. Conversation about something.
Oh, yes, we can hear you. Can you hear us?
Economics were putting on a grant that I was leading.
Yeah.
And at which point, and she was insisting that they should.
Oh, that was okay.
Hello?
Hey, Shulin, can you hear us?
Yeah. I'm here. I'm happy to take questions here. Yeah.
Okay, great. Do we have questions in the audience for Shulin?
Hi, thank you for your presentation. I was just wondering, I didn't see in the presentation, what's the motivation or what is the privacy leakage that we need to protect regarding K-sets and K-clicks? Is there a very good use case where the protection of these specific structures is really important or more important than protecting single links between two nodes? Thank you.
Thank you for the question. I don't think it's more important than the only info link between two particular nodes, but we think it is also important to infer the substructure, like the clicks or the key hop paths, for example, on the romantic relationships, like user A and both user A and C, they want to keep their relationship confidential, but it already engaged with another person B, so this person want to keep their relationship private. And another example is some products from biomedical companies. Maybe their product can be represented as graphs. Like some other companies may want to infer the substructure of their graphs. This may leak the property information, intellectual property of this company. And from another point of view, we also
compare our method with the method which only infer the link between two nodes, and namely we first infer the relationship between two nodes, then based on the inference, we infer the subgraph structure of the clicks and key parts, and we found that this method has a lower attack performance than our method. Yeah, thank you for the question.
Okay, thanks. And I have a question for you. So I was a bit surprised when you said that you were able to add noise to the least informative features in the graph embedding. So I understand why that would be desirable to preserve utility, but I was, could you give some more intuition for why that works to confuse the inference?
Oh, yeah. Thank you for the question. First, our inference is based on the similarity between the posteriors. And when we add the noise to the least important ones, the similarity between the similarity between the posteriors will be influenced by the least important dimensions. So this is why the inference performance is decreased, but the utility is still preserved.
Okay, great, thanks. And we have time for one more question if there is one. Okay. Qiling, thank you again.
Thank you. Thank you for your attention.
Okay, and for our last talk, we have Hao He with the George Washington University.
Good morning, everyone. This is Hao He from the George Washington University. Today, I am presenting our work on a black box edge privacy attack on graph neural networks. Let me first introduce the background. Graphs exist and are widely used in different domains, including molecules, knowledge representation, and social networks. GNNs are neural networks specifically designed to handle graph data. In this slide, we present the fundamental framework of a two-layer GNN. The input to the GNN is a graph along with its node features. Within each layer of the GNN, node features are transmitted through edges to neighboring nodes. Each node updates its features by aggregating the features received from its neighbors. This whole operation is called message passing. The output of a GNN will be used in various downstream tasks, such as node classification, graph classification, and link prediction. In this paper, we focus on node classification. Common types of GNNs include GCN, GIN, and GAT. These models primarily differ in their methods of feature transmission and aggregation. GNNs have a wide range of applications, including recommender system, traffic prediction, and drug discovery. This work is motivated by a real-world example. We have two types of entities, companies or departments. In this scenario, Alice is a company that holds social network data, which is graph structure, and Bob holds user properties, which are node features and labels. Bob wants to enhance their service by leveraging users' social connections. However, due to privacy concerns, the information cannot be directly shared between Alice and Bob. To address this, they deploy a GNN model on a machine learning platform, allowing Bob to obtain predictions through an inference API without directly accessing Alice data. However, this model is still vulnerable to privacy attacks. An attacker, such as Mallory, can exploit the inference stage to reconstruct a highly accurate approximation of Alice's proprietary edge data by utilizing the inference API. Moreover, Mallory does not need Bob's access privileges. The attack is feasible As long as Mallory has access to the inference API and knows the node identity. In our paper, we show how Mallory can achieve her goal by providing our link inference attack, MAUI. Here, let me formalize the threat model. The attacker's goal is to infer whether an edge exists between a pair of nodes in the target graph. The attacker's capability includes the knowledge of node identities and the black box access to the inference API, including the output of prediction probabilities. Let me introduce the framework of MAUI. The first step to attack is to initialize random node features. Here, all the nodes share the same feature. Without extra knowledge, this process may require multiple tests and adjustments. If the attacker has the knowledge of some node features, they can simply apply the features to every node. Second, we estimate the influence value of a node pair. The influence value represents the influence of one node to the other through a GNN. In this figure, we want to estimate the influence value from node 1 to node 0. We remove other node features, get the prediction of node 0. Then we remove the features of node 1, find the prediction of node 0. With the predictions, we can calculate the influence value from node 1 to node 0 by L2 norm. Finally, we repeat the step for all the node pairs. With all the influence values calculated, we reconstruct edges for node pairs with the top k influence values. Since each node can have an arbitrary number of edges, the influence value vary across nodes. As a result, comparing influence values between different nodes is not meaningful. Therefore, using a top k strategy to attack the entire graph is not accurate. To standardize this distribution, we apply min-max normalization to influence values of each node as our global attack strategy. Given that the minimum influence value for each node is 0, the normalization equation can be simplified by removing this term. We provide 3 estimation strategies in total to balance the attack performance and time consumption for different situations. The original MAUI framework can be time-consuming since we need to call the inference API for every node pair. The efficient strategy can estimate the influence values from one node to other nodes collectively with limited API calls. The combined strategy uses the efficient strategy to filter out unnecessary node pairs, then applies the original strategy for the remaining node pair. The details of each strategy can be found in the paper. For our experiment, we use 6 datasets in total, 2 small graphs and 4 relatively large graphs. We use different GNN models, including GCM, GAT, and GraphSage. We apply 2 defense mechanisms, left graph and edge attention. Edge attention is proposed by us. We choose average precision as the primary evaluation metric due to the significant sparsity of positive labels in an adjacency matrix. Our work is compared against 3 baseline methods. It is important to note that each of these baselines requires additional attack capabilities. For example, LSA2 requires node features. We evaluate attack performance under both local and global attack scenarios. For small datasets, we perform attacks on the entire graph. For larger datasets, we conduct attacks on 5 randomly selected subgraphs. Here we share the performance of local attacks with two-layer GCNs. For local attacks, we compute the AP for each node and then average the results. It is evident that MAUI significantly outperforms other baseline methods, with a considerable gap between it and the others. For a global attack, the upper section is the performance without our normalization strategy, and the lower section is under our strategy. Same as local attack, MAUI achieves the best results. It is also evident that the normalization strategy greatly improves the global attack. This is the result of global attack with normalization strategy. Here we show the precision and recall at different ratios of predicted edges. Overall, our method achieves the best and the most stable results. Finally, we compare the performance of MAUI using different estimation strategies with two-layer GCNs. The figures illustrate the attack performance. The use of efficient strategy does not have a large impact on performance. The GitHub dataset contains dense and sparse subgraphs. However, in practice, we can adjust the hyperparameters to achieve the optimal results. In this slide, the figures display the running time. We can conclude that the efficient strategy significantly reduces time consumption without a large impact on performance. In practice, we can adjust the use of efficient and combined strategies for the best outcome for larger or denser graphs and deeper GNNs. Only the efficient and combined strategies can complete the tasks within a reasonable time frame. To conclude, we have demonstrated that a vertical partition of graph data and a black box API could leak privacy. We have designed a link inference attack, MAUI, which attacks under the most challenging security setting. We have provided different strategies to improve the attack's applicability. We have evaluated the attack performance across various criteria, which are detailed in the paper. We have made our code available on GitHub. The artifacts are evaluated to be functional and reproducible. If you have any questions, feel free to contact me. Thank you all for listening.
Okay, thanks, Haoyu.
Hello, everyone. I'm happy to take any questions.
And it sounds, do we have Haoyu?
Can you hear me?
Yes, we can. Do we have questions? Thank you very much for your talk. Do we have questions in the audience? We have time for a few.
I want to. Yes.
So one thing I was wondering about is with respect to your performance evaluation you did you showed towards the end. And I was wondering, you measured the attack performance in terms of seconds, but could you say a little more how that translates to like what the attacker is actually doing in that time? And is it submitting some number of queries? And are you assuming that this is happening locally or interacting with some model hosted remotely?
So for the time for each dataset, we attack the whole dataset, and then we report the whole time frame we need to attack to get the results. So for the attack, we submit the node identity and node feature, the random node features to the API, and then we will get the result from each node pair. And after completing all the node pairs, we are going to generate the time frame.
Okay, so is the time in the attack more related to the time it takes to query the model, or after you've queried the model, the inference time is the thing you're measuring, or both?
It's actually both, the whole attack.
Okay, great. And I was also wondering, the other attacks you compared yourself to, like decoder or link teller, are those also black box attacks, or are those model aware attacks?
For the decoder is not a black box attack. It needs to access the node embeddings before the prediction. And for the link teller, their motivation is actually very similar to us, but their attacker has to access the node features.
Okay. Is it surprising to you that you're able to achieve similar or better performance to them in a black box setting?
Yes, it's actually surprising to me.
Okay, thanks. And are there any other questions in the audience?
Hi, do you actually have an idea how to defend against this without degrading the graph? Like, did you do any preliminary experiments or something that could hint into any direction?
Yeah, we have proposed a defense mechanism, which is not showed in the slides. So basically, we try to, the GN use the message passing technique. So what we do is to add some noise to the message passing, and then we kind of twisted the attention between the on the edges. So for predicting a node, we basically need to utilize all the edges. So by twisting the attention, I mean, we can use several important edges, and disregard other unimportant edges. Also, we have the noises, which will be a good defense mechanism against the attack. However, so far, there is no specific mechanism against this kind of attack. This can be a good future work direction. Thank you.
Thank you. Okay. Well, thank you again, Haoyu.
Thank you so much.
And that concludes our session. So up next is lunch, and I believe that's where you registered. And we will proceed with the next technical sessions, I think at 1:30, so in an hour and a half. See you then. Thank you.
So much. Right, yeah, no worries. No worries.
Check my connection.
Yeah, sure. Yeah. Feel free to plug it in.
Okay. How about this one? Okay, so I need to plug something over here. Okay.
You could move closer to the center. Everybody will be able to get a seat. Okay, welcome everyone to the session on mixing intersections and unions. And without further ado, I will hand over to the first speaker, David Budas.
Hello everyone, welcome to my talk. Today I'm going to talk about provable anonymity guarantees for continuous stop and go mixins. They have been around for 25 years, more than 25 years. They have also been deployed in practice by name technologies, but till now we didn't know if they actually can provide provable anonymity guarantees or not, or there are no rigorous formal security analysis for these kind of designs. This work has been done with Claudia Diaz, Agalos Caius, and Thomas Zacharias. So when we talk about provable anonymity guarantees, generally we define anonymity in terms of indistinguishability-based definitions, where in a global passive adversary tries to identify between Alice and Bob, who among them has sent a message, where the adversary observes the network as well as the recipient might have been compromised. And the probability that the adversary detects correctly should be less than the probability that the adversary detects wrong, plus some slack factor delta, which is a function of the security parameter. And sometimes we want delta to be negligible, and then we call it strong anonymity. In this specific case, we are talking about the anonymity of the sender. That's why we're calling it sender anonymity. For this talk, we'll talk about anonymity notions that are related to sender anonymity or that are similar to sender anonymity. So the mixednet protocols that tries to achieve provable guarantees, they typically use some form of rounds. So for example, in this case, Alice, Bob, and Thomas sends messages together as a batch. And they also do layered encryption. And in the first round, the first layer, the mixed node on the first layer receives all the messages. And then it decrypts one layer, shuffles, and then forwards to the second layer in the next round. And in the next round, the next mixed node operates, and so on. And finally, probably the adversary is confused about which message was sent by whom, as long as at least one of the mixed node is honest. This we understand that, okay, if there is at least one mixed node is honest, that have shuffled, which we don't know how the shuffle has happened. However, how does continuous stop and go mixednet works? In case of continuous stop and go mixednet, each message is delayed independent of all other messages, following some probability distributions. In this case, we analyzed exponential distribution for delays. And then the hope is that during the time the message is in the node, probably some other message could have mixed with that. And some people also claim guarantees based on things like, okay, since exponential distribution is memoryless, if two messages come at time T1 and T2, and then one message leaves at time T3, you don't know if the message leaving at T3 came at T1 or T2 because of the memoryless property. However, it's possible that the first message could have left much before the second message has arrived. Or in general, the end-to-end delay for the mixed net, that itself is not exponential distribution, that is an Erlang distribution, because it's a sum of all the exponential distributions. And Erlang distribution, it is not memoryless. And of course, there could be compromised nodes. And then the question is, how do we prove anonymity, or what this leaks, this Erlang distribution? To analyze that, as a first exercise, we wanted to analyze something we call FIFO attack, or first in, first out attack. So what's the setting? Each message is delayed following exponential distribution with parameter lambda. And users are also generating messages at a rate of where the time between two messages follows the exponential distribution with parameter lambda u. And in this given example, suppose the first message from Alice comes at time T1, the second message from Bob comes at time, T0, the message from Alice comes at time T0, the message from Bob comes at time T1, and we want to calculate the probability that they preserve the order or they don't preserve the order. And we did not want to choose a specific good or bad setting. Rather, we wanted to do expectation over all possible such differences. That's why we chose such a distribution of sending messages. That Alice sends following the distribution, Bob sends following the distribution. And then what is the probability that they will swap order? Or what is the probability that they'll keep the same order? This is the probability that they will keep the same order. Let's try to understand this equation, right? Come on, no, I'm not going to do that. Instead, we coded the equation in a program and we plotted the equation. Here, rho is the ratio between lambda u and lambda. That means rho higher means that the users are sending messages more frequently. That means with high probability, the gap between the two messages is small. And if you can see for a small value of rho, the probability is significantly high compared to 0.5 for the adversary, for them not to switch order. However, if you increase the rows significantly, and also if you increase the number of hops significantly, then it is coming close to 0.5, which is possibly good, but still even for number of hops 20 or number of hops 40, the probability is something like 0.501 or something like that, even for row equals to 64. So that could be somewhat satisfactory, but some people might be purists say, okay, 0.50 is still large, at least in the asymptotic sense. We did not do an asymptotic analysis. We did concrete analysis for this case. We did not want to analyze that equation. However, that means this could translate to attack in the real mixnet. And for the first definition that we consider, we call it pairwise unlinkability. This is similar to sender anonymity, but there are subtleties. For example, we assume that the adversary has background knowledge about when the challenge message has been created. So in this example, Alice and Bob are sending messages, and then the adversary says, this is when the challenge message have been generated. And that means if Alice and Bob, one of Alice and Bob has to send a message, the immediate next message from Alice or Bob would be the challenge message. And then they can possibly use the FIFO attack. And why this is relevant? This captures scenarios like whistleblowing, where the adversary might intentionally plant a message and see how the users react. This is a strong scenario, but this could still be relevant to capture such adversarial knowledge about timing when message is generated. And if the adversary has such knowledge, in that case, we had a really depressing result where with only 5 mixed nodes per layer, even with no compromised nodes in the whole mixnet, still the success probabilities of the adversary is greater than 0.9, which was really depressing. And I have to specify that this is upper bound. We also derive lower bound, but upper bound is the one which you can claim as the security guarantee. And then we ask, like, then should we give up, that there is no hope? And then we say that what if we take away the knowledge of the adversary, the background knowledge about when the message is generated? So in that case, the adversary is basically, suppose Alice sends a message and the adversary wants to track that message, how it goes to the network. And just based on that tracking, the adversary wants to break anonymity. And then can we get better results? And this is typical to tracking scenarios. For example, typically in the network, the adversary sees a message on the recipient side and tries to backtrack who has sent the message. And we also do further relaxation that as long as the message from Alice mixes with any message from Bob, then we can call it that it is achieving anonymity. So that means all the messages generated by Bob are honest messages. And the adversary doesn't have background knowledge about those messages from Bob. And in that case, we get a pretty hopeful result. This is the upper bound on the success probability of the adversary with 5 mixed nodes per layer and with 10% compromised nodes. And still we show that there is drastic decrease in the adversarial advantage delta with the number of hops. So that's hopeful, so probably that's achievable. So the key takeaways from our work is you can achieve strong user unlinkability, but not so much about pairwise unlinkability. And of course, this work is not complete. There are so many things that are yet to be done. I mentioned about the background knowledge of the adversary, that the adversary knows exactly when the message is generated in case of pairwise unlinkability. In case of user unlinkability, we completely take away that knowledge. But in reality, there might be a scenario where the adversary has partial background knowledge. How do you capture such notion? And exactly how to model and what kind of, how much knowledge to assume, and then what kind of guarantees can you provide? That is one interesting direction that we plan to continue working on. And then how do cover traffic impact those guarantees? With that, that's all I have. I would highly encourage you to read the paper for the actual proof and derivations, and if you have some questions.
Thank you. Any questions?
Yes. Yes, it's a global passive adversary. We did not consider active attack. Yes.
Sorry, I'm a little bit late, so I missed the very first part of this presentation. So my question is, how do you define that strong user linkability? Do you have like a formal definition of it?
I did not present the definition.
Can you just quickly explain what kind of intuition behind it? How do you like model the strong user unlinkability? Sorry.
User unlinkability is the definition. Strong means that the delta is negligible. That's the strong part. User unlinkability is basically Alice is sending messages, Bob is sending messages, and we assume that all the messages from Bob is honest. Now Alice sends a specific message and it pops up on the recipient side. The recipient is compromised and the adversary recognizes this is the challenge message. And the question is, then the adversary tries to figure out if which message from Alice is or is it Bob or Alice sends the message. And that means as long as any Alice's message mixes with any message from Bob, then basically you achieve mixing. So it's basically between indistinguishability between users rather than messages. Does it answer your question? Or maybe we can discuss about the definition later. Yes.
And some plots I've seen that basically you had a lot of hops and each hop has this like Poisson distribution or Poisson distribution for like delays. Does it make it impractical? I mean, I want to catch a website and not wait like super long for it to load.
Now you are asking the question if do you want to implement a mixnet using Poisson distribution?
Yeah.
And what kind of application can that support? We do not answer that question in the paper. Yes, that's a different question in terms of practicality of mixnets and what kind of applications it can support. But the thing is, those designs are there and people are using those designs. Now we want to know if it is secure enough to use those designs. Of course, your question is valid, but we do not answer that question in this paper.
Okay, thank you.
Any other questions?
You say people are using these designs. Your distribution sometimes had like 50, 100 hops in it. You're telling me that people are using mixes with where there's 100 hops in the message chain?
No. Okay. That was just to analyze like what kind of hops should you choose or what kind of security guarantees you get. Not,
okay.
That was not the intention.
Okay.
Yeah.
While Philip's setting up, there's some more chairs on this side of the room, so anyone who's in the stairs, you can come down and then go around, if that would help.
On the front?
Yeah, and then the front's open as well. Okay. Okay, thank you. So next talk in this session, provable security for onion routing and mixed network packet format Sphinx.
Cool. Thank you for the introduction. I'm Philip Scherer from KIT, and I have the pleasure today to present to you our work on provable security for the onion routing and mixed network packet format Sphinx, joint effort with Christiane Weiss and Thorsten Struve. So, Sphinx. When we're doing onion routing, mixing, we need an underlying packet format that can actually, carry our data through the network. Sphinx is one of those formats by Danetsis et al., and it's compact and provably secure, which makes it interesting. As a quick refresher on onion routing and also an introduction to our notation, we're interested in obscuring sender-receiver and sender-message relationships, and the way we accomplish that is that when we have multiple users like Alice and Carol trying to send messages to Bob and Dave, they send their message through multiple relays, and if they share an honest relay, In our notation, adversarial relays are marked in red, honest relays are black. If they share an honest relay, then the attacker won't be able to link what comes out of that honest relay to what went in. And so that's how we hide our links. Now, there are two different ways to construct these networks. We call them the integrated system model and the service model. In the integrated system model, the receiver is itself part of the network. So in this case, Bob is itself a relay in the network. While in the service model, receivers are external to the network. So there might just be like normal web servers, and instead the final relay in the network is responsible for communicating with them. This may seem like a minor difference, but it will turn out to be very crucial right now, because unfortunately Sphinx is susceptible to a malleability attack. In Sphinx packets, only the path information in the packet that says, which relays we're routing through is actually protected by a MAC at every hop, while the payload's integrity is only verified at the very last relay. This is due to technical reasons with the packet format's construction. What it means is that the adversary can flip bits in the payload of the packet to effectively tag it. This completely destroys the payload, but at a later point in the path, like for example here, if the adversary tags Carol's packet, and then we have Dave, who is an adversarial receiver, receives the packet, sees that the payload fails the integrity check, and now knows that Carol was trying to message him. So now we have a global adversary that can link senders and receivers, which is exactly what we were trying to prevent. This problem affects several protocols that use the Sphinx format, including Hornet and Taronet. However, Sphinx wasn't actually originally designed for the integrated system model. It's actually a service model format. And when we try to perform the same attack in the service model, we see that the integrity check will now fail at the final relay, not the receiver. And since the payload is destroyed, which also contains the receiver's address, now the attacker doesn't actually learn anything useful. They only learn the link between the sender and the final relay. Under the assumption that the final relay is chosen randomly, for example, that's useless. So what are we trying to do? We could mitigate the tagging attack. There are approaches to do that, but they either have massive costs and efficiency or impact the packet format's functionality. So instead, what we're going to try to do is prove that Sphinx is secure in the service model. There are a couple steps to doing that. First, we need to actually provide a formal definition of onion routing and mixing in the service model. Then we need an analytical framework to actually compare Sphinx against. We need to make an adjustment for Sphinx to actually be secure in this framework. And then we need to do the proof. And the result will be that we'll have provable security for a highly efficient OR and mixing packet format. So about the whole adjusting Sphinx part. Sphinx supports replies, so receivers can send replies back to the senders. This is done via anonymous return envelopes that the sender prepares beforehand. In the original construction, Sphinx uses a NIM server to implement these replies. So the senders actually send two packets. One is the regular packet that goes through the normal path to the receiver, and the second one goes to the NIM server and contains the return envelope. The NIM server will then store the envelope, and when the receiver wants to reply, it sends its reply message to the final relay, which forwards it to the NIM server. The NIM server will assemble the packet from the return envelope and the message and send that back through the network. This is susceptible to a tagging attack, the same one we were talking about earlier. If we have an attacker that tags the packet containing the return envelope as it leaves the sender, then the NIM server will receive a destroyed payload, and so it won't be able to store the return envelope, which means that later when the final relay forwards the message, there won't be anything to pair it up with, and an attacker-controlled NIM server or an attacker that can observe most of the traffic of the NIM server will then be able to link the sender to the final relay and thus the receiver. We get around this by removing the NIM server from the network. Instead, we take the return envelope and put it in the payload and just send it to the final relay. This eliminates the separate packets we were sending to the NIM server at the cost of increasing our payload sizes. So now we've adjusted Sphinx. We need an analytical framework so we can actually, prove anything. The existing frameworks for onion routing and mixing don't account for the malleability with tagging or for service model networks. So we need to make a new framework. For that, we adapt Kunet Al's framework for the integrated system model into the service model. This comes with 3 game-based onion properties and 1 ideal functionality. And in combination, the properties, which are comparatively easier to prove, are sufficient to realize the ideal functionality, which would be more difficult to prove directly. And now all that's left is the easy part. Full security proof. Sphinx did originally come with a security proof. However, that one was based on incomplete properties that weren't sufficient to actually prove security. So we make a new detailed proof based on our onion properties in the new framework. In doing so, we make another discovery. The original underlying assumption for Sphinx's security was the decisional Diffie-Hellman assumption. We also discover that that's insufficient. So we switch to the gap Diffie-Hellman assumption, which states that the computational Diffie-Hellman problem is hard even when you're given a magical DDH oracle that solves the DDH problem for you. The good thing is the gap Diffie-Hellman assumption is generally assumed to hold in standard elliptic curve groups, which were already being used with Sphinx. So this doesn't actually, you don't have to change the implementations. You're just using a new assumption. And with that, we have the first full detailed security proof for Sphinx. There are some things you need to be careful about when using Sphinx to do it securely. First of all, yes, you have to embed the return envelopes in the payloads, as mentioned earlier, because using the NIM server would allow for the tagging attack. The NIM network, which also uses Sphinx, already does this. Their return envelopes are embedded in the packets. And secondly, as mentioned before, the tagging attack does still allow you to link the sender to the final relay. So that link must not reveal critical information. So your choice of final relay can't depend on the sender or the receiver or the message, but you can choose final relays randomly or based on load balancing, for example. So, and with that, we reestablished Sphinx as a provably secure base for onion routing and mixed networks. In summary, we provide the first formal definition of service model onion routing and mixing, an analytical framework for onion routing and mixing packet formats in the service model, an adapted version of Sphinx that works in this model where we embed return envelopes and payloads instead of sending them via the NIM server. Then we provide the first full detailed security proof for Sphinx in this model based on the gap Diffie-Hellman assumption, and we provide criteria for secure usage of Sphinx. And if you're still interested, then check out our paper. Thanks for listening. Mike is moving towards you.
Nice talk. I like these results. You mentioned that there's an attack on Sphinx packet format based on the reply going through the NIM server. Was there a fault in their proof, or did their security properties not address this scenario?
The security properties were incomplete in multiple for one, they're not sufficient for the packets themselves, and they also don't account for the existence of a NIM server.
I see. Okay.
So yeah.
Thanks.
So you say NIM already did this. Did they know or suspect, or did they, for logistical reasons, not use a NIM server and they got lucky, or?
I haven't asked them. I suspect they did it for logistical reasons, because the NIM server is also a central point of failure in the network and a pretty juicy target for an adversary. It's a server that every reply message goes through.
Harry from NIM. I mean, I think that the issue with NIM servers is that's a really old design that's kind of email based, and Lupix et al. Like they don't use NIM servers. They just use normal serves. You can drop them off at gateways or mixed nodes or whatever. So I did actually. I mean, I also noticed it was a bit odd, not because just like common practice. Like, why would you not integrity check the payload? Did like George just forget, you know? And it is like George Denises is not an idiot. I did ask him this question, and he basically had a counter argument, and it's related to the email issue, where he basically said, well, if you do an integrity check and you're under this kind of active attack, then the packet just gets dropped, right? So you don't know you're under attack because Sphinx was invented for email. If someone did do a bit flipping attack and the receiver received garbled text because the decryption didn't work, then they would know they were under active attack. So that's just so you know the reasoning for George's original design decisions there. I was wondering though, like, I guess you don't get to in this paper, in terms of Sphinx, do you think that this do you really like how, in terms of like the proof, how much of the effort was based on doing multiple hops? Because Sphinx was originally for free routing, and it seems like that general design has been thrown out by the community, in which case maybe simpler designs with simpler proofs could be possible.
So yeah, there's a couple things there. The first thing about the whole like integrity of the payload thing, we also looked into like there are multiple approaches to addressing the whole thing, and they each have their drawbacks. So like so for example, there is work that like provides integrity on the reply path, but then that starts involving things like zero knowledge arguments, and things get expensive really quickly. And so like also for practical reasons, it's hard to offer integrity on the reply path. For your second question, sorry, I forgot it. Could you repeat it? Oh yeah. Yes. Yes. So the proof as it stands works for both models, but yeah, we chose to go with like the very generic approach. I'm not sure it's actually that much harder necessarily.
Online from Ian.
Hi, thanks. So I'm the et al. On the original Sphinx paper. So to address Harry's question about the integrity of the payload, the speaker just referred to it briefly now, but the primary reason that the payload is only end-to-end or sender to exit node, but not recipient, authenticate or MAC'd is exactly because you can't MAC the replies because you don't know what they're going to be. And so only the sender can put the MAC on the replies, which can only be checked at the end. Right? The nested headers can't include any information about the replies because the nested headers are created in the PI on the slide on the screen right now, and that's before the reply body is known.
Thank you for your input.
Yeah.
Great to hear from you.
Okay, thank you. So next talk, traceable mixed nets. Over to you.
Thank you very much. Hi, my name is Prashant, and I will be talking about this new cryptographic primitive we have introduced in this paper called traceable mixed nets. This is joint work with all these nice people. One of them you'll find somewhere here. So the agenda today is I will introduce traceable mixed nets and contrast that with traditional mixed nets. And then I'll go over the key challenges in building traceable mixed nets, the key techniques we use, and some comparisons with existing techniques. And then I'll talk about applications of traceable mixed net in the context of voting, in particular, how to recover from failures in large elections. A mixed net is a primitive used for anonymous communication. In particular, it takes as input a list of ciphertexts which encrypt some sensitive content like a vote in an election. And the ciphertexts are usually tagged with some metadata information about the sender. For example, the identity of the voter or the place, the booth they are voting from. And the mixnet actually is, it consists of multiple mix servers. Here I am just showing two, M1 and M2, which successively permute the list of ciphertexts and finally produce a permuted decryption list. And the guarantees that it provides is it's verifiable, that it can prove that the output list is indeed a decryption of a permutation of the input list of ciphertexts. But also mixnets are completely untraceable, so that assuming that at least one honest mix server exists, the association between the ciphertext and the plaintext cannot be identified at all, and it is completely untraceable. So untraceability is indeed a gold standard, but sometimes in some applications, some form of controlled traceability is also required. And this is what is the focus of this paper. And we formalize this controlled traceability in the form of special queries that we call trace in and trace out queries. So let me just explain what I mean by trace out. So a traceout query takes as input a plaintext in the output list of the mixnet and a set of ciphertext in the input list of the mixnet, and answers the question whether the plaintext was encrypted in one of the ciphertexts in the input list without revealing which ciphertext indeed. And this gives you a proof of provenance of the plaintext item. And symmetrically, a tracing query takes in ciphertext from the input list of the mixnet and a set of items, a set of plaintext items from the output list, and answers the question whether this ciphertext encrypts one of the items in the set without revealing which one. So this is a form of proof of eligibility or membership of the ciphertext of the sender. And the main challenges in giving these kind of answering these queries is verifiability. And the mixnets have to verifiably answer these queries and not just know the answers to those queries themselves. They have to prove it to a verifier. Secrecy, no additional information apart from the output of the query should be revealed. And what makes this kind of proof very difficult is because this is a distributed proof. So none of the mix servers by themselves know the association between the ciphertext and the plaintext, yet somehow jointly they should prove statements about it. And that makes this challenging. And finally, what we are after in terms of efficiency is batch efficiency, which means that if you run multiple such queries, for example, a traceout query, if you run multiple of them against the same set, then we want such batched executions to be efficient. And as you can perhaps imagine, a naive repetition of multiple traceout queries could be quadratic in the size of the mixnet input list, but we want the entire batch query to be linear. So traceable mixnet is essentially, these are mixnets that address these challenges precisely. They are mixnets that provably answer batched trace-in, trace-out queries efficiently, which means linear in the size of the input list, and without leaking any additional information. So before I go further into the construction of traceable mixnets, I want to spend a minute into what are the secrecy properties of traceable mixnets especially in the presence of these additional queries, and how they should be deployed. And of course, because we support these additional queries, they leak more information than a completely untraceable mixnet. So what queries to be allowed should be decided at an application level, depending on the application level secrecy requirements. Given a set of queries, there should be a privacy risk analysis step which identifies what is the privacy risk with allowing these set of queries. And we give some framework in the paper. And after this analysis, query access policy should be decided, which decides who gets to execute what queries. And the traceable mixnet basically guarantees that the query access policy will be faithfully followed. In particular, what we guarantee is that no query is answered unless all mix servers agree to answer it, which prevents against bad queries. The querier doesn't learn any more information beyond the output of the query. And this last one says that the mix servers don't even learn the query output. So in this sense, the mix servers answer the query obliviously. And this is required to prevent mix servers from accumulating query responses given to different queryers over time, and then completely learning the link between ciphertexts and plain texts. But this property prevents against that. Okay, so now let me describe some key techniques behind our construction. So the tracing query is enabled by a popular zero-knowledge proof in cryptography, which is called zero-knowledge proof of set membership. This is a proof that takes a commitment as an input and a set of plain text values as input, and answers and proves whether the commitment commits some value in the set file without revealing which value it commits. And this is a well-established proof. We, in fact, give another zero-knowledge proof, which we rather uncreatively call zero-knowledge proof of reverse set membership. So a ZKP of reverse set membership takes a plain text value and a set of commitments as input and proves whether some commitment in this set commits the value without revealing which commitment. So the traceout query is based upon the ZKP of reverse set membership. And so far, these are single prover proofs in the non-badged setting. So one important extension in the paper is how to make them distributed and how to create badged versions of these zero-knowledge proofs. Unfortunately, I will not have time to go over how we make that construction, but I will provide you some comparisons with existing techniques in the literature. In particular, we compare with respect to three main metrics. What is the complexity of giving the badge proof, whether the technique supports reverse set membership, and whether it supports single prover or distributed provers. So the first technique that may come to your mind is the standard OR composition of Sigma protocols, where you can prove that a commitment commits a value in the set by proving that it either commits the first value or the second value or the third value and so on. And you can imagine that for a batch proof, this will be quadratic overall. This supports reverse set membership also because it's a generic techniques, but unfortunately, this is only a single prover technique. Similarly, you can use ZK snarks and Merkle accumulators, which provides order n log n complexity for a batch proof. And since again, this is a generic technique, supports reverse set membership, but it is a single prover technique. There was this interesting approach by Kamenish et al. In 2008, where the proof that a commitment commits a value in the set involves proving that I know a signature on the committed value. So one proof was order 1, which gives an order n complexity for a batch proof, but this was an interactive proof. And since this was a specific technique, it doesn't support reverse set membership. It was only for set membership. We actually extended for reverse set membership. And this was also a single prover technique. So, and in the setting of distributed provers, there was recently work on collaborative ZK snarks, which generically extend ZK snarks. So it retains the asymptotic complexity of ZK snarks, and this is our main comparison point. We actually extend from the signature-based set membership proof technique and add support for reverse set membership and make it distributed. And in terms of comparison with collaborative ZK snarks, our technique is 86 times faster set membership proof and 18 times faster reverse set membership proof. And the implementation is completely available in this link. All right, so now let me come to the application in terms of failure recovery in elections. So in elections, usually typical scenario is that voters go to cast their vote and their encrypted votes are at the beginning of the mixnet, which may contain information about which booth they voted at and so on. And the mixnet permutes and decrypts the votes. But asking for a large election, asking the election authority to completely rely on cryptographic voting is very hard sell. So it is often also required to maintain a paper audit trail where paper votes are also separately kept. But now we have a problem because if there is a mismatch between the electronic votes and the paper votes, then you cannot resolve these disputes. And because of the untraceability property of mixnet, you can't even identify where these failures originated from. So in fact, this is what we do with a traceout query. You can actually consider the set of votes that were cast at a particular booth and then answer whether this discrepancy was originated in that booth without revealing any additional information, specifically without revealing which voter it corresponds to, and without even revealing the booth level voting statistics. And we present more sort of similar recovery use cases in this paper, which was published in eVote ID 2023. And this is, so the traceable mixnet enables these kind of generic localized recovery use cases. So that's all I had to say. Open to any questions.
Hi, great work. I was just curious, you said at the beginning that you need to establish what queries you're allowed to set. So I guess in the setting of this election is quite clear because there's one election council and they decide what queries. But say you have like a system where your aim is not about verifying like elections, like you just say sending emails, right? So at some level, all the users or someone has to decide what sort of, for example, the size of the set that you're allowing, right? Because you could just have one as well. And you'd be like, well, it's not in the set, it's just this particular entry. And then maybe you de-anonymize someone because of that reason, right? So I'm just curious, like, do you think it's like what practicality there is in trying to establish these query sets and how you might go about doing that?
Yeah, I think that completely depends on the application. And in the case of voting, it depends on, where the failures happened and which booths you suspect and so on. So it is very application dependent. Yeah, so you have to do that application dependent privacy analysis.
Okay, thank you. So now we have towards a practical multi-party private set union. Over to you.
Thank you for the introduction. I will present our paper today about practical multi-party private set union. This is the work done with my labmate Xiaohui and my supervisor Nichio, and I'm Son from Arizona State University. So the talk today will consist of 6 parts: introduction to the problem, some applications of MPSU, the challenges that we face, some related work, the construction of our protocol, and the results. First, the introduction to MPSU. So in the problem, we have multiple parties, each have a set of elements, and at the end of execution, you will have one party we label as leader to learn the union of everyone's set. The goal is to hide all the partial union between any parties and the intersection items of the party to the leader. So the leader will only learn the union at the end without any additional information. It has multiple applications. One of them is joint IP blacklist computation, where you have multiple service providers, each have a set of IP addresses that they want to block, and together they perform some service. So they want to have a union of the blacklist, and they use that to block in further services. There are also other applications shown in this slide, ranging from private database supporting full join to distributed network monitoring or even federated learning. Even though it is very useful, it has many challenges compared to the peer two-party PSU. One is that you have to hide the source of the data point in the union. So in two-party case, if the receiver received the union and the element in the union is not in his set, he will know that that element coming from the sender set. And it's no point to hide the source of the data. But in multi-party case, you have to hide the source because you want to prevent the partial union leakage between him and the other parties. And the second challenge is you have to hide the duplication. You have to handle the duplication of the data points. So when you have multiple senders, there are cases where the element comes from more than one sender, and you have to hide how many senders sending that elements to the leader. Because of those challenges, and although it is very useful, multi-party PSU is not really focused, and you see a lot of work on two-party PSU, but not multi-party PSU. Among the related work, we find there are 3 major approaches: a polynomial-based PSU, where they use homomorphic encryption, which is computationally expensive; sorting-based PSU, they use MPC to sort the list of all elements in an MPC, and then remove duplicated elements. This is very communication expensive because you have to do the sorting. And finally, Bloom filter-based PSU, where they use local and global Bloom filter computation and later compute the union based on the filters. This is all both computation and computation expensive. So we digress from all of the existing approach. We take another approach where we label one party as leaders, and the leader will expand the set by sequentially interacting with each party and accumulate the union set. We do so by using 2 building blocks. One is membership oblivious transfer, and second is oblivious shuffle and decryption. Before we come to each building blocks, I want to review a bit about two-party PSU reverse private membership test, which we base our approach on. So in two-party RPMT base, the receiver will learn a bit B of whether the element Y in the sender set is in its set or not. And based on this B, sender and receiver will interact in an OT to learn the final union. This bit revelation B will actually reveal the additional information. But it's okay in terms of two-party PSU because at the end you will learn such information from the results. But it's not okay in MPSU because you have to hide the partial result between the 2 parties. So we solve the problem by having a secret share. So instead of the receiver learning the bit, we have the sender receiver each receive one binary share of the bit itself. And based on the binary share, they interact in the OT to have the receiver learn the correct message. And we name this as membership OT, which is short as MOT. The second building block is software and decryption, where we use a traditional multi-key scheme, and with additional functionality, we name re-randomization, where we take the ciphertext and the public key, but we output the totally new ciphertext. And this new ciphertext is the same encryption of the same message, but the value is totally randomized and different from the original one. Based on such multi-key scheme, we build the shuffle and decryption, where we have each party PI come up with a random permutation PI. And first they permute the set of ciphertext they receive, and then they partially decrypt the set of the ciphertext. After that, they randomize the message. So at the end, you will have a new set, completely new set of ciphertext, which is one lower level in terms of partial decryption you have to do. And the order is totally different. The appearance is also totally different to the next party. So PI will forward such output to the next party. So here's an example of how it works. It's a simple example where you have three parties. P1 have a set X1, P2 have set X2 of one element, and P3 have X3 of one element. And X2 and X3 are equal to each other, and X2 is not in set X1. The first interaction is an MOT between P1 and P2. Because, so P1 as the receiver and P2 have two message encryption of X2 and encryption of 0. Because X2 is not in the set of the first party will receive the first message, which is encryption of X2. He will expand the set of the union to accumulate the new message that he received, which is encryption of X2. This set at the end will be shuffle and decrypt and finally reveal to the party P1 what is finally the union. At the same time, P2 and P3 also interact in an MOT. So because X3 is in the set X2, so P2 will receive encryption of 0. And after receiving this, he will re-randomize the message, send it back to P3. P3 receive this message and replace M0 with this message. And you can see in this slide, P3 now have two messages. One is the re-randomized version of encryption of 0 and encryption of 0. So both of them are encryption of 0. And even though at the end of protocol, P1 and P3 interact in an MOT, and X3 is not in set X1, X1 will just learn the encryption of 0. And we add that to the final set E. And they do at the end, P1 call decrypt and shuffle to every parties, and he will learn the decryption of E, which is X2 and 0, but in totally permuted order. And he joined that with X1 to have the final result of the union. The example is simple as it only have one element per set, but you can do couple hash and simple hash scheme previously proposed by the two groups. And the protocol introduced above can be performed rather easily in the same manner. Note that we can also use batch membership tests, so in order to achieve the better complexity. So here's the performance. You can see that our protocol are the best running time in both the LAN setting and WAN setting, while we are the second best in combination cost. Thank you for your attention. And you can find the code.
Thank you for the talk. There is an underlying assumption that there is a ground set in which all the private sets are embedded. So in that case, I wonder if you also compared your solution or the other solutions to the most naive approach in which you compute the union set by performing OR. If the ground set is not too large, perhaps that simplistic approach of computing ORs is even more efficient. Have you considered that?
Yes, so in the paper, we actually mentioned about the case where you have like the universe of the items and you run the PSI on that. And it is okay in terms of the universe size small, but yeah, we actually discussed it in the full paper, so you can find it.
Thank you.
Yep. One part that I think I missed. Do you reveal the size of the data sets of individual parties?
Oh, yes. So there's an assumption that the size of everyone should be the same. But if they are not the same, then you just part in dummy values to the set.
Okay. Yep, thanks.
Who's got the outline question? Or
sure. Does your protocol work in the malicious model or the semi-honest model? Like the shuffle and decrypt, does that have to be verifiable?
So a disclaimer that I'm not the first author, but from what I understand, it only works in semi-honest model.
Okay. And in your three-party example, each party talk to each other party. In an n-party example, is it do you still have n-squared communication, or do you just need communication like around a ring or something?
I think we need to have every party, like every pair of parties talking to each other, unfortunately.
Okay. So a lot of communication.
Thanks.
Any other questions? No? Okay, let's thank speaker. Taking last talk in this session, mix match flow matching for mixnet traffic.
Yeah, thank you. Hi, I'm Leonard. I'll be presenting mix match flow matching for mixnet traffic, and this is work with Mark, Enrique, and Claudia. And this paper investigates the question how well a state-of-the-art mixnet, in this case we analyze NIM, prevents passive gateway adversaries from linking communicating endpoints using only the packet metadata. So this comes down to the timestamps and the size of the packets that they send. A little bit of background on NIM. What is NIM for us here? NIM aims to be a general purpose anonymous packet routing layer for a large share of applications that can communicate over the internet. In terms of its mixnet properties, it's a continuous time mixnet. That means it treats each packet independently. It doesn't assemble them into batches. And it also enforces pretty strict, or it stipulates pretty strict traffic shaping properties for endpoints that are connected to it. Specifically, endpoints will shape their traffic to follow a Poisson process that they send through NIM. Relevant for our work is that we use NIM as the stand-in for a state-of-the-art mixnet. Because its code is available, it is a deployed system and it's under active development. To visualize this just a little bit, you can see here many of the relevant parts of NIM's infrastructure, specifically on the left-hand side, the users and the service providers, which we just call endpoints because their role doesn't matter to us. On the right-hand side, you see the mixnet, consisting of the mix nodes that is responsible for anonymizing the packets. And in between, there is an interface layers of nodes called gateways, and they keep some state for the endpoints connected through NIM. They will also, I understand that eventually they will be billing them and so on. And these nodes are really relevant for us because we assume that the adversary is running some of them. and conducting the flow matching attack at this point, right? So the adversary is internal, running some of the gateways and matching flows at this point. How can the adversary do this? In the paper, we discuss two traffic features that can be exploited to conduct flow matching. The first of them is shape, we call it shape. And it's really what you would expect of it. It's the intuitive notion of like seeing how traffic progresses over time and then matching based on similarity of like how similar they look. So I hope you agree with me that it makes sense to guess that egress 2 is the egress flow for ingress and not egress 1, right? Because of how similar their shape looks. Indeed, there's previous work in the context of the anonymity network Tor that exploits this traffic feature shape, specifically the two systems Deep Coffee from 2022 and Deep Core from 2018. And they are also really relevant for us because they were the foundational papers in the space to use deep learning methods for the traffic correlation setting. We adapt Deep Coffee into our deep learning classifier that we call Shape, very original, to test how well the best attack against Tor works in the much more difficult context of mixnets, specifically again NIM mixnet, right? However, as I already mentioned, NIM enforces pretty strong traffic shaping behavior of endpoints. Remember, they will shape the traffic to follow a Poisson process, which means that shape features are strongly, like heavily diminished, right, in terms of like how much you can exploit them for a flow matching. So the adversary will might need the secondary one or a different one, and this is drift that we also discussed in the paper. So when endpoints send their packets following a Poisson process, this means that they will, on average, send constant bandwidth through NIM. And if you think of like two NIM endpoints that are connected through NIM, you can think of this visually as like a pipe of a known constant diameter through which they will send their packets, right? Like going in and coming out. And if that is the case, we can expect that their difference in timestamps of the egress timestamp and the ingress timestamp at the same position in the sequences, that this follows a known and low variance distribution. And we can visualize this so you can see the difference quite clearly. The delay distribution for matched flow pairs is shown in blue and differs like significantly from the delay distribution of unmatched flow pairs in orange. And we can use this to build a test that says, okay, does a test flow pair like correspond to the expectation? In this case, we classify it as matched. If it doesn't, it's unmatched. And the naming comes from the delay distribution drifting away from the expectation. That's the idea here, right? We use this to build two classifiers. The first of them is called statistical, and it models this drift distribution explicitly, and then computes likelihood scores for the candidate pairs. And the second classifier is called drift. It is a deep learning-based classifier that learns the underlying distribution of the drift from the large data sets instead of modeling it explicitly, right, using a convolutional neural network. We have to make two important assumptions for the setting of flow matching. The first of them is that the sets of endpoints under consideration are expected to communicate exclusively among themselves, right? That means these sets can be of any size. They can be of like size 2, size 5, size 10 or more. However, you cannot have any out of set packets. So any kind of packet that is part of the evaluation needs to be within the set of endpoints under consideration. We propose a technique that we call flow merging that enables us to transform the flows that we collect for our evaluation to be much more usable with our classifiers. So you can see on the left-hand side, this is the representation of the independent flows for three endpoints connected to NIM. And then you can transform these three independent flows into a joint merged representation that works nicely with our classifiers and also gives us the ability to take care of NIM's loop cover traffic because NIM sends a type of cover traffic that loops back to the sender. The second big assumption is that any packet sent is assumed to be eventually received within the set. So for a large part of our data sets, we assume that there's no packet loss. And I can go into a little bit of detail later. So we evaluate our three classifiers, shape, statistical, and drift, using 6 data sets, out of which I will only discuss 2. The first of them is called baseline. It is a default NIM configuration, so we don't mess with packet timings or sending behavior in a lab-like setup, in an isolated setup where there is no propagation delay and no packet loss.
And we do this so that we can focus on the core contribution of the mixnet to the anonymity or to the protection against the adversary in this case. There's 4 more data sets that we collect, but I will not go into detail here. You can find the results in the paper. And then the second relevant data set is called LiveNIM. It is again default NIM, so unmodified sending and delaying behavior. However, this time it's not in the lab-like no network effects setup, but on the live deployed NIM network. So that includes propagation delay and packet loss and other network artifacts. Let's look at some results. Our result plots are receiver operating characteristic curve plots. So that means we show the true positive rate versus the false positive rate. Mind that the false positive rate is a logarithmic scale. And we plot the performance of our classifiers here. And specifically, we always want to be at least better than the random classifier, which is shown in green. And the best classifier would be in the top left corner. That would be a perfect classifier. And what you can see here is that the more data that we feed our classifier, so this is the number of observations going up, the better the performance, the flow matching performance gets, until ultimately we reach almost perfect classification. However, noteworthy here is that even only feeding 100 network observations already yields relatively good performance. Specifically a true positive value, a true positive rate of 0.6 for the drift classifier, 0.47 for statistical classifier, at a false positive rate of 10 to the power of -2, which is already quite good. We don't show the shape classifier here, as you might have noticed, because initial evaluations showed that it underperforms the other 2 classifiers significantly. So we focus on the 2 better performing classifiers for the majority of our plots. However, not for the next plot, which contrasts the dataset baseline and the dataset LiveNIM that I introduced earlier, right? So remember, this is both default NIM, but once without any network effects, once with network effects. And we can see that the shape classifier is in both cases is much worse than the 2 other drift-based classifiers, right? However, maybe even more relevant here is that the introduction of like real-world network effects has a significant impact on our classifiers, which like reduces their classification performance, which we attribute to these network effects kind of like invalidating the flow matching assumptions that we make for our classifiers, right? What our classifiers are based on. Okay, so this impression gives away the primary idea for a countermeasure to a flow matching attack against mixnets, which is to invalidate the exclusive communication group assumption, trying to introduce cover traffic that is not seen by the adversary, so that the adversary would have to increase the observed the test of the set of endpoints under consideration if it is even visible to the adversary. This could be achieved through 2 means. You could send cover packets that are supposed to be dropped along the mixnet path somewhere, like one mix is instructed to drop it, or you could send cover packets that are addressed to as large number of random endpoints as possible, as well as receiving from as large number of endpoints as possible. With this, I'll go to 4 takeaways from this work. First of all, mixnets are a powerful tool for network level privacy, but they were designed for single packets or short flows, not the long flows that we see from like any modern application workload that you send through the internet. The second takeaway is that under the assumptions that I presented, our attacks are fast and accurate, which shows that even a modern and like state-of-the-art mixnet such as NIM is not immune to this de-anonymization threat. However, this setting of like long flows, or like let's say just regular flows nowadays, plus an adversary that is internal to the system sitting at both ends of the connection, right, at the gateway position, is very hard to protect against, and we need more research to work on this open problem. And the final point is that the difficulty of the classifiers with missing packets indicates an avenue for a countermeasure to our attack, to this attack, specifically to break this endpoints closed set condition. With that, I thank you, and I'm ready for questions.
Hey, thank you very much. This is really cool work. So I really appreciated takeaway 1 because in the previous talks, I was only thinking about single messages when we were talking about mixes. And I wasn't really sure how flows work in NIM. So is it like, do all the messages between two communicating parties go through the same series of mixes, or is it something else?
They don't go through the same series of mixes. Each packet takes its own path through the mixnet, so each packet will use its own cryptographic key material and take its own path. They are only streams or whatever at the endpoints, right? So they go like, okay, it depends on how many gateways you connect to, but assuming that you connect to one gateway, this would see like all the packets in between that link, but then through the mixnet, it's one path per packet.
Thanks for the talk. You mentioned that there are network effects that invalidate your classifiers. Did you look into that? Do you know exactly which effects those were? And could you say more about that?
So invalidate in the sense that they diminish the classification performance. They don't like break them entirely.
Yeah.
And we also think that there might be ways for how we can like be better in those cases, right? But the assumption is that any kind of network effect like packet loss, for example, of course invalidates this assumption that every packet will eventually be received that is sent within a set, right? Of course, the packet loss invalidates this, which makes the classifiers based on drift struggle because they don't have a perfect ingress-egress packet index match anymore, right? So those are the network effects that we are talking about.
Is there do you have analysis in the paper on the performance in the face of those real-world conditions that you can't get around?
Yeah, so the data set live NIM captures these, right? So we show the performance in this setting. So yeah, some analysis of this is part of the paper, yes.
Thank you.
Yeah, so on that note, this is Harry from NIM. Could you describe what was the baseline again?
Baseline was like default NIM, no changes to how packets are sent or delayed in an isolated setup, which means no propagation delays, no packet loss.
So was that the NIM software or was that a simulator?
It was NIM software. Yeah.
Okay, so you're running NIM software on your own controlled environment.
Yes, indeed. It's a single host.
Yeah. No, I mean, that would make sense. So, I mean, it's interesting. I mean, in live NIM was just whatever we were running at the time you did the attacks.
Well,
which I think was the unparameterized testnet with no adaptive cover traffic.
It's the live deployed mainnet that we hooked up our private data collection.
Yeah, I'm just going to note that we haven't added cover traffic or adaptive cover track to the mainnet, and we didn't parameterize the mainnet. So you're essentially running like live NIM is whatever random parameters Anya Petrowska chose half a year ago whenever you did this work, right? So it would be interesting maybe to try, for example, longer mixing parameters, more cover traffic, adaptive cover traffic, which is what we're working on now with Carmela. I think would probably help. We also noticed that in our work with Carmela, which is we're doing a poster session on that. Actually, I mean, Tor is great, performs in the real world actually a little bit like a mixnet, just because there's fragmentation on the traffic level, right? That being said, very good work. I would suggest for future work of this type, running it on the actual parameterized network and not random test nets.
To clarify, we ran it on the mainnet.
Yeah, but if you run a network on like an imaginary environment, then it's like you get imaginary results. And then the second thing I would point out is that like your threat model is pretty strong. So I think it's a true threat model, but like it's not surprising. I think it'd be the same with Tor, that if you control both the entry node and you assume that all the traffic is going through one entry node, and you control the exit node, and you can assume all the traffic is going through that exit node. So both entry and exit adversarial, and you're running machine learner over long sets of traffic, like of course the attack will work. So I don't think the result is, I mean, we didn't consider it very surprising, and it would be equally devastating to Tor or like any other system.
100%, like no question for sure. I think it's a realistic threat model in the sense that the adversary only needs to run some gateways, right? It's not assumed to run all gateways or even to be able to see all traffic, not at all, right? It's only able to conduct these kind of attacks on the traffic that it is able to observe at its own gateways, which, you are able to run gateways on the main net. So it's possible for an adversary to get into that kind of position. But yes, of course it is, it comes with its own set of strong assumptions for sure.
sounds like an interesting discussion to have over the break. But before then, we've got our final talk of the session, which is recorder section. So could someone cue that up, please?
Hello, everyone. I'm Jeffrey. In this video, I'm going to present our work, multi-party private set intersection cardinality and its applications. This is a joint work with Nichu and Avishai Yanai. And this is the content for the presentation today. So private set intersection is a well-studied problem in the context of multi-party computation. This figure shows a two-party case where the receiver and sender each have private input set X and Y. And the receiver should learn the intersection of these two sets, while both of them learn nothing else apart from the final output. In this case, the result is P and S. And private set intersection cardinality is something different. Instead of learning the actual intersection elements, P and S, in the previous case, here we only want to learn the size of the intersection set. In this case, it's 2. For our work, we consider the PSICA problem in the multi-party setting. So the PSICA have many applications. The first one is called dot product. So suppose you have two binary vector V1 and V2. We can convert these two vectors into two sets by recording the non-zero elements position in the original vectors. And then compute the PSICA functionality on these two sets will give you the value 2, which is the product of the original vectors. Another application is called heat map detection. So consider a scenario where the Department of Health and Human Service want to learn the area where there's a higher chance of getting affected with the disease without knowing the travel route infected individuals. So basically, the HHS have a data set which is a vector X representing a positive patient of a specific disease, such as COVID-19, where in this vector 1 means the specific person have been tested positive, and 0 means negative. For the network operator's input, which represents a location, such as a building, it also maintains the same length of binary vector, where 1 means the user had been visited this location and 0 otherwise. So the dot product for the red vector with any blue vector gives you the number of positive visitors to that location. By aggregating all the results for each blue vector, you can construct a heat map look like this. So instead of doing that by aggregation of personal travel route for infected people, you can do it in a privacy-preserving way, as I just introduced. So here are some previous work for PSICA protocol. The first work is KS05, which is the polynomial-based method with homomorphic encryption. So in their design, each party represents the set as an encrypted polynomial, and then they aggregate the polynomial to compute a global one, and then they evaluate their own private input on this global polynomial under the additive homomorphic encryption. The decryption of the number of zeros will give the number of intersection cardinality. The inefficiency is from the homomorphic encryption. MRR20 is one work requiring 3 non-closing server compute the PSICA functionality in a secret sharing way, and it has a large communication cost. The state-of-the-art multi-party PSICA comes from the work of CDG21 by conducting the multi-party circuit PSI, where the party align the data using the cuckoo and simple hashing technique, and the leader conduct the circuit PSI with each party, and then from the share received of these pairized invocation, cardinality can be computed from the MPC technique. But that also introduced heavy computation and communication cost. Before we introduce our design, here are some preliminaries. The first one is called Oblivious to Random Function, OPRF, which is a 2-party protocol where the receiver have a query X and the sender have a PRF key K. And the receiver will learn the PRF value of the query X with respect to the key K, while the sender learns nothing. So oblivious programmable pseudorandom function OPPRF gives an advanced feature to the OPRF. So here the sender can additionally have a set of key value pairs, in this case yi and vi. So instead of directly learning the evaluation for the PRF of query X, the receiver will learn vi if the query X equal to any of the key yi in the sender set. And this key value store, which is a technique, can realize the functionality of OPPRF by encoding the key value pair into a data structure, which leaks no information for the original input, while can allow other parties do the decoding given the key. The simplest construction for OKVS is a random polynomial. The unconditional zero sharing is a multi-party protocol where all the parties agree on the sharing function S, and each party PI learns a key KI. So for a input value X, the party PI can compute a random share for X as SKIX. If this X is the same for all the parties, then the share will be X or to 0. So based on what I just introduced, we propose two new building blocks, the server aiding OPRF and server aiding OPPRF. So for server aiding OPRF, we consider a double key PRF where the FKX is equal to the FK2 and FK1X. So in this case, the sender have the key, which is a pair K1 and K2. The sender send the K1 to the receiver and the K2 to the server. And then receiver can compute the first layer of the PRF, which is FK1Y, and send it to the server. And server can return back with the other layer of PRF. And we realize this functionality can be easily extended to a server aiding two-party PSICA protocol. So instead of directly sending the PRF evaluation of the receiver set Y, the server send back the permutation of it. And at the same time, the sender can send the PRF value of his set X, and then the receiver can compute the cardinality of these two sets, which is equal to the cardinality of the original input X and Y. We also have something similar for OPPRF in a server aiding setting. So please refer our paper for more details. And now we are ready to introduce our main construction, which is a serverless multi-party PSICA protocol. So the idea is like for a element X belongs to Xn, we want to check whether this X also belongs to all the other parties through P2 to Pn minus 1. And if yes, then Pn will learn a PRF value of this element with respect to key S. And at the same time, P1 can also compute the PRF value of his input set X using the same key. And then P1 and Pn can invoke the server aiding PSICA protocol to compute the cardinality of these two sets of PRF values, where P2 can play as a server. In the previous mention, the server aiding two-party PSICA protocol requires non-gluing server. So in this case, for multi-party setting, we require the P1, P2, and Pn are not glued as well. So the first step for our main protocol is to invoke the unconditional zero sharing protocol among P2, P3 through Pn. Each party will learn a key Ki, and they can compute the secret share for each of their input values as S. And at the same time, the P1 and P2 agree on the secret key S, and they can compute the PRF value for their own input set, X1 and X2. And then each party compute the value V as the share, where the P2 compute the V as the XOR of the PRF value and the share. So for the next step is to invoke the server aiding OPPRF functionality, where before that, each party agree on the key K and then compute the PRF value of their input over this key K. So for PI, they place as the sender. The key will be the PRF value for the input, and the value will be the V from the previous step. The receiver will be PN with the input of the PRF value of his input and learns the output WI from this functionality. So ideally, if the query belongs to one of the parties' input set, the WI will be the corresponding share. And then the PN compute the XOR of all the sharing. So ideally, if everybody have an element X, then the corresponding value WJ will be FSX2. And finally, P1 and PN can invoke the PSICA protocol with the helping server P2. So here we show the performance comparison with previous work. To compare with CDG21, we run our protocol in the full party cases with different number of elements in each set. To compare with the MR20, remember our protocol requires P1, P2, and PN not colluding, which is the same as theirs require 3 non-colluding servers. And both comparison shows we have better running time and communication cost. Thank you so much for your listening. If you have any questions, feel free to ask. Thank you.
Presenter is online if anybody has any questions to ask.
All right. Thanks. I think you had a question.
So earlier in this session, we heard a talk about private set union, and 2 sets of co-authors have a non-empty intersection. You are one of those, one member in that intersection. I wonder, in that talk, the techniques that you presented, are they applicable also to private set union, or does the union computation introduces different challenges?
So the question is about the difference of PSSE and PSU, right?
Excuse me?
So your question is about the difference of PSU protocol and PSICA, right?
No, I'm wondering, you have presented here a method to compute the cardinality of the intersection. If you want to apply this to the problem of union, would it be direct, or does the union computation introduces other challenges that require some different techniques?
Okay, I see. So thank you for your question. I think in general, the union requires more challenge for sure, because when you consider the intersection, all the party already have the input, let's say, from the perspective of P1, in this case, to be the leader. P1 already have any element in the intersection. So, but for the union, P1 should learn some new elements. So in general, no matter you're considering the union problem or the union cardinality problem, the leader will require to learn some extra information from all the other party in the setting of union. So I believe probably we cannot directly apply the technique for computing intersection to the union in this case.
Thank you.
Yeah. Any other questions? No? Okay. Well, let's thank the speaker and all the others of this session.
Good afternoon, everybody. Welcome back. Welcome to the session on data privacy. So let me introduce myself so we can gain some time before people arrive. My name is Zeki Erkin. I'm from Delft University of Technology, and I will be chairing this session. We have so far 5 speakers available, so we are still missing one. So hopefully we will get that person on time. But the first speaker is with you. Are you ready for your presentation? Okay, then the floor is yours, but expect some people, interrupting slowly.
Sure. Should I use a mic? This one is okay. Yeah, I hope you can hear me well. So hello everyone, I'm Guipo. So today is my pleasure to present our recent work, Fat Lab. And this is a joint work with my amazing colleagues, Dimfan, Ralph, and also Mario. So let's first begin with some background. So as you already know, deep learning has sort of revolutionized the world. We already have a lot of interesting applications like segmentation or ChatGPT, or even diffusion models for image generation, or even video generation. But this all comes at a cost. For example, the demands on computation resources has been significantly increasing in the past around 10 years, and it's even faster than the Moore's law. And moreover, the amount of required training data set is also increasing exponentially. So I would say this kind of bottleneck needs to be considered for the future applications. So as a remedy, federative learning proposed by Google a few years ago enables users to jointly train a model without sharing their data with each other. So typically, this framework is realized by the following steps. First, the clients can first train their models locally using their private data for a few local steps, and then they only share the gradients with the central server. So as long as the server receives the gradients, they can use it to, for example, taking average over the received gradients and then update the global model. And they just broadcast the updated model back to the clients and repeat this process until, for example, the model converges. While it sounds quite promising and actually has been implemented in many real-world applications, it actually is still facing a lot of challenges. One of the most critical ones is optimization over non-IID data and also differential privacy. So this kind of non-IID data would typically yield inconsistent objective functions and also deviating gradients. Sorry. Okay.
Try this one.
All right, sorry for the technical issue. So basically, this non-IID optimization problem can be briefly described by this equation. So we can see here, as long as you optimize your local models on your local private data for a few local steps, the resulting gradients will be different from the global gradients, which, for example, if you gather all data together and then directly optimize the model. And this is simply because the local objective function is consistent with the global one. And to give you an illustration, for example, you have 2 clients. Each of them has either, say, all cat or dog images. And then if you train model on these clients and then simply take averages over them, then you might result in, I don't know, in the middle of nowhere instead of the desired cat-dog classifiers. So, and furthermore, if you want to introduce more theoretical privacy protection like DP, you will further amplify such deviating gradients and makes the problem even worse. So to mitigate this challenge, we let's first take a closer look at this equation. So the problem comes from the inconsistency between the objective functions. So if we can find an approximation to replace this bias loss function, then if with such an approximation, we can sort of convert the problem back to centralized learning. And so in this work, we try to propose novel optimization methods that can find a proper approximation. And then in the meantime, we also want to retain privacy protection. And also, we don't want to introduce additional communication costs. The idea is that since the gradients could be biased because of the biased local data set, we try to communicate local loss landscape. And the idea is that we can actually synthesize a small set of images that will deliver gradients that is similar to the one generated by real images. And after, so in each communication round, the clients just send these images to the central server. And once the central server receives these synthetic images, they can train the model as in centralized learning. So with such strategy, we can avoid bias optimization caused by the non-IID data or gradients DPSGD. I won't go into the mathematical details about how we achieve optimization, but basically, we first of all, we need to measure the gradient similarity between the one generated by synthetic images and also the real images. And since we don't want to introduce additional communication cost, we can only maintain a small set of images. So in this way, in this scenario, we only approximate a small neighborhood, which is measured by the distance between the updated models and also the initialization. And lastly, in each communication round, we also do sort of meta updates to mimic the optimization on the server side. And then we just communicate such synthetic images. And once the server receives that, they just do things like you do in centralized learning, but following the radius or neighborhood is defined on clients. And then to further integrate theoretical privacy protection like DP, we simply need to replace the real gradients part. We first use DPSGD, use DP algorithms to sanitize real gradients, and then we just follow the same procedure as we described before. And due to a nice property of DP, post-processing theorem, we can show that any downstream optimization won't breach the protection, which means that the generated images can be freely shared anywhere, and any potential privacy leakage will be upper bounded by the privacy budget you set at the first place. So in the experiments, we test our method on 3 common benchmarks, and also we consider 5 clients, and each one has 2 disjoint classes out of total 10 classes, which would result in a very extremely non-IID case. And we also consider a few common baselines, which are kind of state-of-the-art for in FL. And then for DP settings, we just apply DPSGD to these baselines. So let's first begin with the non-DP experiment. You can see here, first of all, our methods performs quite well, outperforms the baselines, or just comparable to the baseline, but incurs require a similar level of communication costs. And another interesting point is that we found that our method typically learns faster and more stable compared to the baselines, which probably can be attributed to this non-biased optimization. And we move on to DP settings, where we consider epsilon between 2 and 10. This range is kind of widely considered in industry. For example, from Google, in some Google or Apple's product, they consider this range. And then we see that for most of the cases, our method outperform the baselines, and especially under tighter privacy budget, our method is performs much better than the baselines. And to verify the privacy protection property, we also conduct membership inference attack against all of the baseline and also our method. So first of all, we see that it's not surprising that with DP, both gradient sharing methods or our method are quite robust against membership inference. But more surprisingly, in even non-DP method, our method seems to be also more robust than gradient sharing method. And this can be potentially attributed to post-processing theorem because we add one more step to distill the training information. So in summary, we propose an interesting novel optimization method that mitigates non-IID data optimization. In the meantime, we also provide, it's still compatible with DP and provide theoretical privacy protection. And then we can remain a similar level of communication cost. And yeah, so in the experiments, our methods performs quite well. But lastly, we hope our work can sort of motivate the community to think about or investigate more novel optimizations for FL problems instead of just sharing gradients. So that's it. Thanks for your attention. If you are interested, you can refer to our paper and also GitHub code.
Perfectly on time, so even with a delay. Do we have any questions from the audience? Yes.
Hi, thanks for the great talk. I was wondering, how are you generating the samples on the client that you then send to the server? Are you just using like a GAN that gets random noise as the input during the generation?
So, so first of all, in this case, we don't really need realistic images. So in this case, we simply use backpropagation to learn, to update the images. So to be more specific, we can start from initialize these synthetic images with real images or simply from random Gaussian noise. And then we just use Gaussian optimization, backpropagation to update the images according to these objective functions.
Okay, thank you.
I see another question here, please.
But I take to use some information only available at the client to make these images. You can't just send the gradients to the server and let the server drive synthetic images. So what information from the client goes into this?
Do you mean the optimization part or the radius part?
The generation of these synthetic images that is sent to the server. If I didn't misunderstand it completely.
Okay. So you mean what kind of like information I send to the server in the end, or?
Yeah.
Okay.
Yeah.
So first of all, we will send the synthetic images because from this, because our goal is as long as you have this set of synthetic images, you can derive gradients from this set of images. And so in this case, you just need to send these images to the central server. But in non-DP case, you can also, so for both DP and non-DP case, you can also set a radius, which can be kind of hyperparameters. You can, so both server and clients can communicate at the beginning, even before the training started. So in the end, two kind of information.
I think I need to stop here so that we can move on to the second speaker. Is it okay if you continue during the coffee break?
Yeah, so if you have any question, I'm happy to answer during coffee break.
Great. Thank you very much for your presentation. You're the third speaker. Okay, good. By the way, can I ask you people move to the middle because there are people sitting on the stairs because no one can get in. It will be super nice if they can also have a seat. Okay. Are you ready?
Yes. Yes,
Please
I'm ready.
introduce yourself as well.
Of course. Thank you very much.
The floor is yours.
So, thank you everyone. I am Eber Wanger-Kolesi, and I'm happy to present a paper we had with my collaborator Sebastian Gams. And the paper is about revealing the true cost of locally differentially private protocols from an auditing perspective. So to start with some context, we saw already many types of audits from the keynote of Natalia this morning, from the previous talk. And what we can conclude is that they are the backbone of accountability and trust, because we can somehow make some form of a systematic review of the system, of a model, to ensure the compliance with standards and the achievements of objectives. So you can imagine this is widespread from many industry. It's not about only privacy, it's in healthcare or accounting and finance and so on. So the motivation from privacy auditing is, here is a non-exhaustive list. We can use it to uncover vulnerabilities to further prevent privacy breach or other privacy incidents. We can also use it to ensure compliance with data privacy laws that we saw in the keynote this morning. We can also use it to evaluate the robustness of the privacy model we have, such that we can test it against the state-of-the-art attacks. So why do I mention privacy attacks? We can use it because it's a way to ensure that we detect the vulnerability of current privacy techniques to the state-of-the-art attacks. So for instance, we saw some papers about identifying the failures of pseudonymization and further inventing k-anonymity. And later on, we saw some paper proposing some attacks like homogeneity attacks to k-anonymity methods and further inventing error diversity. And so on until we arrived at some point with some reconstruction attacks to aggregate the statistics, which inspired the invention and adoption of differential privacy. So we all know a bit what is differential privacy, and what we'll be talking is about the local model of differential privacy. So which means that the differential privacy model is moved to the user's device, which means that we are protecting from different data points. So we can imagine to any inputs V and V prime in the domain of the mechanism, and we have any output Z. We want that the ratio between these two probability events to be bounded by E to epsilon. So bounded means this corresponds to a theoretical upper bound. So many works in LDP will try to propose a new LDP mechanism such that they comply with these provable upper bounds. So some audit questions that may arise is that, are these bounds always tight? Or for instance, can we get some form of empirical privacy for a mechanism when we use state-of-the-art attacks? Or even if we don't have some formal proofs for an LDP mechanism, what happens if we try to estimate some form of lower bound? So this is the role of differential privacy auditing in the literature, which is some form of, for instance, had been used to assess the tightness of a differentially private mechanism. And tightness means that the practical or empirical epsilon will correspond almost match the theoretical epsilon. Or in some cases, it can be used to assess the empirical privacy. So in this case, we are using real data points, which are not always worst case. So which means that the empirical or lower bound epsilon will sometimes be smaller than the theoretical epsilon that we have. Or in some cases, it can also be used to detect the bugs, because not all privacy proofs or implementations are correct. So whenever we detect that the empirical epsilon is higher than the theoretical epsilon, this corresponds to a bug. So now let's move on to how to audit local differential privacy. But first of all, let's remember how to audit differential privacy. So we saw from the previous talk that we can use some form of a membership inference attack in centralized differential privacy. And in differential privacy, we consider two neighboring databases that differ on the data from a single person. So the distinguisher is basically trying to infer, has this computation been on the database with my target on or not? So we can formulate differential privacy as some form of hypothesis testing. So for the attacker is basically trying to infer it has an output either drawn from MD or from MD prime. So for every attacker A, we will have some form of true positive rate, whenever the attacker guesses correctly. And whenever D prime has been used, but the attacker has guessed that D was used in the input, this will correspond to some form of false positive rate. So we can get some form of empirical lower bound from this, and this corresponds with our empirical epsilon. So we did the same for local differential privacy, and in this case, it corresponds to input value. So it's either V or V prime used in the input of the mechanism. So the distinguisher is trying to distinguish which value has been used. So we formulate LDP as some form of a binary hypothesis testing, where the input has been either V or V prime, and the attacker will either guesses correctly for and guesses as a 2 positive rate, and if the attacker guesses incorrectly whenever V prime has been used but it guesses V, it will correspond to some form of a false positive rate. And in the end, we have the empirical lower bound. So what we proposed is essentially this, which is an LDP auditor. We start with a mechanism. It can be an epsilon LDP mechanism or not. We fix 2 different inputs, V and V prime, and we run some attack, and we fix the output, for example, to V. So whenever the attacker guesses correctly, we have the true positive. Whenever the attacker whenever we use V prime as input and the attacker guesses V, it's a false positive. But a single run will not be good enough because we have a lot of randomness in the mechanism, in the attacker. So we have to done a lot of, because we are trying to statistically measure differential privacy. So these will come up to Monte Carlo methods. So in the end, we will have some true positive rates and false positive rates. And this is used to estimate the empirical privacy epsilon that we have. So I talked about the attacks. So basically in LDP, we have the user's value uses some form of a local differential privacy mechanism and generate Z. So the server or the attacker looking only at Z and knowing how the mechanism works, it tries to predict what was the input value. So the distinguishability attack we talked before. But the problem is that we have a lot of different LDP mechanisms because they have different encoding, or sometimes they have the same encoding, but different perturbation parameters. So it means that the proposed attacks in the literature, they were tailored for the LDP mechanism question. There is no fit at all attacks for this type of thing. It's not like the membership inference attack we have for a machine learning algorithm. So here's an example of just 2 LDP mechanisms. One of them has been used in Google Chrome, which is based, for example, on one-hot encoding, and we have some perturbation of the bits independently. So in the end, the attacker with this information, it will try to predict what was used as input. Or another mechanism, for example, use some form of local hashing for going from one domain to another domain, and then the attacker using the information of the bit which has been perturbed to achieve LDP, he or she will try to predict what was used as input. So let's get a sneak peek of our contribution so far. So let's set up, for example, epsilon as a theoretical epsilon equal 2. And we have experimented here, in this case, with 8 fundamental LDP protocols. The names are here, but it just means that they use different encoding and perturbation. So what we found is that sometimes the empirical epsilon for some mechanism was less than 2 times the theoretical 1, or even 4 times the theoretical 1, which means that we get different auditing results because they have different encoding and perturbation, which means different attackability for this LDP mechanism as well. So the only LDP protocol that yields some form of tight empirical estimation was the well-known randomized response that some of you might know. So some hypothesis that we formulate is that either the state-of-the-art attacks are not strong enough for these protocols, or in some cases where the encoding has some form of randomness, like local hashing, there might be some privacy gain in this encoding instead. So as one of the case study, we have asked if we could use our tool to also detect some form of bugs in state-of-the-art LDP package. So for our lucky, we detected a bug in an LDP Python package, which is called pure LDP, and the LDP protocols which were used were based on one-hot encoding, and they had different perturbation parameters. That's why we have symmetric and optimal unary encoding. So we found that in this orange box, you can see that the empirical epsilon measured was higher than the theoretical one. So this corresponds to an epsilon LDP violation. And we reported the missing step in the codes to the authors, and they already fixed this in their new version. So we had many more case studies in the paper. I invite you to read if you're interested. We also considered, for example, approximated local differential privacy protocols, non-LDP protocols, and also different cases that are interesting for industry, like longitudinal data, collection throughout time, and also multidimensional data when we have several attributes. So to conclude, what we proposed is some form of a general framework to audit some form of empirical privacy loss for locally differential private protocols. And the main insight is that we not always have a tight empirical estimation. And all these LDP protocols, they differ. So they differ in the attackability, which means they differ also in the auditing. So the findings are generic in the sense that these LDP protocols are building blocks that are used for many tasks, like heavy hitter estimation, marginal estimation, and sometimes machine learning as well. And as perspectives, I invite the community to instantiate this form of LDP auditing to other adversarial approaches that exist in the literature, for example, risks of identification or inference pool, and also extend this LDP auditing to other data or tasks that will lead, for example, for mean estimation that can also be used for federated learning. And we plan to upgrade LDP auditor from artifact reproduced to a general Python package on PyPy. So thank you very much for your attention, and I'm ready for the
Thank you very much. Questions? Oh, please go ahead.
So the LDP auditor that you have, even if it says that there is no problem, doesn't mean the solution is, the protocol is correct, right? You can't find all the bugs because your LDP auditor is just statistically generating a lot of samples and using a Monte Carlo simulation. Am I correct in my understanding?
Yeah, this is exactly the correct insight, because you can see from here that we can detect the bug in high privacy regimes when epsilon is small, because our tool is not specifically for this task of detecting violation. It's just for empirical estimating epsilon. So in some cases, there are some tools like a DP Sniper in the literature that would find the error for all privacy regimes.
So that was my question. So how does this approach differ from those more robust tools that can detect privacy violations across the entire spectrum of the epsilons?
Sure. So our case is more for the case of we are some firm trying to guess what is the empirical privacy of the LDP mechanisms. We're not trying to find a DP violation or to find the tightness of an LDP mechanism. We're trying to see if we can estimate some form of empirical LDP or some form of empirical epsilon for a given mechanism. But yeah, sure, there are some difference. For example, the literature has specific tools for verifiability of differential privacy guarantees, while our is auditing tightness or empirical privacy guarantees of a mechanism.
Yeah, one more question, please. The microphone is coming. By the way, we have two people standing. Maybe you can help them.
Sebastian Hassler from the University of Stuttgart. It seems that your auditor somehow needs to find good attackers because the theoretical epsilon is the maximum epsilon over all possible attackers, and the empirical epsilon is only the epsilon for some attacker which your tool was able to find. And for me, it seems highly non-trivial how you find a good attacker for a generic protocol automatically. So how can you explain how does your tool do this?
Thanks. So this is also a question of ours as well, because we use it what has been proposed in the literature. For example, the attacks for this mechanism corresponds to this attack was proposed in the literature, and different the mechanism, we have different attackabilities. So we don't have a fit-at-all attacks for any LDP mechanism. What we used was existing attacks in the literature. So I'm sorry, but I cannot answer with a completely answer for this.
Well, thank you very much.
Thank you.
Then I invite our third speaker of this session.
Yeah. I have it, but maybe it's okay.
Okay, the floor is yours.
Right. Thank you all for attending the talk today. I'll be presenting our work, A Cautionary Tale, on the role of reference data in empirical privacy defenses. This is a joint work by myself and colleagues at INRIA, SAP, and Accenture. And to support open science, we have the artifact reproduced badge. As the previous talk explained well, differential privacy can be introduced into the training of a machine learning model to protect the data's privacy. And the epsilon that results after using differential privacy can be thought of as an upper bound on the privacy linkage. Also, there can be a practical epsilon that would be assessed using an empirical privacy attack, often a membership inference attack. And this practical or empirical epsilon can be thought of as a lower bound privacy leakage. As these empirical privacy attacks are used to quantify this lower bound privacy leakage, there have been empirical privacy defenses that have been proposed to protect against these type of real world attacks. The most simple example would be just using L2 regularization, where the weights of the model are constrained during training, and this protects the underlying privacy against an empirical privacy attack more than if L2 regularization weren't used. However, there's been many other more complex attacks, more complex empirical privacy defenses that have been proposed, and they often make an assumption that in addition to the training data, they'll use a second data set that comes from the same or a similar underlying distribution as the training data, and this data set would be called reference data. However, despite reference data being integral in the design of many of these empirical privacy defenses, its own privacy has often been an afterthought. Here we can see 6 very well-known empirical privacy defenses in our paper as the 7th on the bottom. We can see that oftentimes the privacy of the reference data isn't discussed or analyzed, or if it is analyzed, it may not be sufficient for reasons I'll show in the next slide. Here, we can see a utility privacy curve that's generated for the empirical privacy defense called adversarial regularization in blue, and a second version of adversarial regularization in orange that we discuss in our paper. We can see here on the x-axis, the model utility or test accuracy, and on the y-axis, the membership inference attack accuracy or privacy leakage. This utility privacy curve can be generated because empirical privacy defenses have a parameter that can be tuned to add more utility or more privacy. However, when looking at this graph, right now we're looking at the privacy leakage only with respect to the training data. And it should be clear that given that the best model would be in the bottom right-hand corner, having the most utility and the least privacy leakage, the orange curve is strictly better than the blue when only looking at the training data privacy leakage. However, these are the utility privacy curves when the privacy leakage with respect to the reference data is also assessed. And what we can see is now no concrete statement can be made about which is the better defense. We can see that the orange curve, it will have better model utility and less privacy leakage with respect to the training data, but the blue one has less privacy leakage with respect to the reference data. So the key point that we want to make is that really, in order to assess one of these empirical privacy defenses using reference data, the model utility, training data privacy leakage, and reference data privacy leakage all need to be assessed and probably explained the training and reference data relative privacy before actually using the method. In order to better understand these empirical privacy defenses, we propose a baseline called WERM. Our problem statement is formulated where we have a data set D that's comprised of the union of the training data, DT, and the reference data, DR. Similar to standard empirical risk minimization, we want to minimize the loss function over LD. However, we introduce 2 constraints. These are constraints on the generalization error with respect to the training data and the reference data, in this case CT and CR. The reason we constrain with respect to the generalization error is because a black box membership inference attack is really trying to understand how the output of a model differs on data that it was trained on compared to data that it wasn't trained on. And this is what the generalization error can quantify, the difference in performance on training data and unseen data. After some manipulation, we end up with this simple equation on the bottom, which is just a weighted ERM, where W is the weight, and W will provide the weight for the L of DT during training, the loss in the training data, and L of DR, the loss in the reference data. So in the case when W is 0.5, this would mean that both losses get equal weight and we're weighting all data points equally. However, if we select a W that's not 0.5, then we'll add some weight, more weight to one of the data sets compared to the other. Why this is a useful baseline and it is interpretable is because it's the first empirical privacy defense that provides theoretical guarantees. First, we provide guarantees on WERM's utility. We derive this equation called N effective, which is the effective data set size. Here we can see that it's solely dependent on W and the size of the training data, NT, the size of the reference data, NR. So when NT and NR are equal, this would mean that using a W of 0.5 would result in an effective data set size being equal to the total data set size, which would mean that the model utility would be maximized. However, using a W in that case not equal to 0.5 would mean that the utility would not be maximal, and then there would be some trade-off with the privacy. So we also derive guarantees on its relative privacy. And this is an important point, that the relative privacy is the relative privacy of the training and the reference data. We're not using this with differential privacy. However, to derive these guarantees, we conduct a thought experiment where we say, what if we train WERM with differential privacy, like DPSGD? Then we would end up with a resulting epsilon value, epsilon 0. And we can see that if we did that, we would derive these epsilon values, epsilon T and epsilon R, which would be the privacy with respect to the training data and the privacy with respect to the reference data. But since we're interested in the relative privacy, by dividing epsilon T and epsilon R, epsilon 0 will disappear. And we see that we actually have these values where it's only dependent on W, the weight, the size of the training data, NT, and the size of the reference data, NR. And what's interesting about these quantities is while we conducted this analysis here for the training and reference data, 2 data sets, these guarantees actually hold for the case where every data point is weighted independently. So if every data point has its own distinct privacy considerations. To better understand these theoretical results, we have this plot where we can see the effective data set size on the x-axis. So in this case, the training and the reference data both have 10,000 data points. And again, the effective data set size corresponds to the model utility. On the y-axis, we have this theoretical privacy with respect to epsilon T and epsilon R, the training and the reference data. And we look at values of W between 0 and 0.5, where 0 would give all the weight to the training data during training, 0.5 would give equal weight. Starting on the right-hand side of the graph, we can see that in the case when W is 0.5, we would expect that the model will have maximum utility because it will weight all data points equally, and therefore the effective data set size will be equal to the overall data set size, and the privacy leakage with respect to the training and reference data will be equal for any value of epsilon 0 if we were to use differential privacy. However, by shifting to the left of the graph, we can see that now we're lowering W closer to 0, and by doing so, we're giving less weight to the reference data, which of course there will be a trade-off because we're going to use the reference data less while training. So it will have less privacy leakage, and that will result in more privacy leakage for the training data and less model utility because the effective data set size will decrease. The reason this is an interpretable baseline is because the experimental results align well with the theoretical results. Here we can see the experimental utility privacy curves with the test accuracy on the x-axis and the membership inverse accuracy on the privacy leakage on the y-axis. If we look at the far right-hand side, where we see the blue curve, this would be our baseline method, WERM, and the furthest point on the right would be the case where the squares representing the training data privacy leakage and the crosses representing the reference data privacy leakage overlap, and we can see that that means that it will have the experimental results show that it will have the largest model utility and the privacy leakage on the two when assessed empirically is equal. And also, by shifting W from 0.5 to 0, we can achieve any possible privacy setting depending on what the relative privacy considerations are before training. Looking at the other methods, these are other state-of-the-art empirical privacy defenses using reference data, we can see that they don't do a poor job of trading off the reference data. So they're not really able to trade off reference data privacy for training data privacy or model utility. So they're only operating in one privacy setting, which is the case where the reference data would be considered extremely private, which is a viable case. But depending on the setting, one may want to consider the other data set more or less private. And it also outperforms these other methods in the majority of these privacy settings. If one were to actually use an empirical privacy defense as a practitioner, it would be important that this desired relative privacy between the data sets that one is using actually has a correlation to the resulting privacy that one would assess with a membership image attack, so that real-world privacy leakage. Here we can see this correlation analysis where, based on the parameter that controls the utility privacy ratio during training for these empirical privacy defenses and the actual empirical privacy ratio as measured by the membership image attack, the RWRM on the data sets we analyzed has a near perfect correlation, suggesting that what the desired ratio that one would want before training will actually result after training. Alternatively, these other methods don't seem to be able to map so well, given a desired ratio to the empirical ratio. So to conclude, overall, we conduct the first comprehensive evaluation into how these empirical privacy defenses perform with respect to all three relevant metrics, whereas previously only the model utility and the training data privacy leakage were looked at. Our method, WRM, is an interpretable baseline that we believe any empirical privacy defense using reference data probably should at least compare against it because it's simple and interpretable. And if it can beat it, then it really shows that the proposed method is working. Interestingly, this baseline actually outperformed a lot of these supposed state-of-the-art defenses, which is exactly why it's important to have baselines and to measure against them. And perhaps most importantly, our theoretical results, they lead to a better understanding of the privacy implications when multiple data sets with different privacy considerations are used to train a single global model, because it can often be the case even in federated learning scenarios where different data sets can be considered having different levels of privacy. And if one isn't using differential privacy, perhaps you would still like to know what is the privacy leakage associated with each of these. Thank you for your attention. I'd be glad to take any questions.
Any questions? No one? Oh, please go ahead. Maybe wait for the microphone for a second. No, for the recordings, we have online people as well. It's coming.
So your approach, does it describe how to actually generate the reference data set, or you assume that there is a mechanism to generate the reference data set?
So we didn't, our approach doesn't propose the notion of reference data. We really took it as a fact in the sense that these are existing empirical privacy defenses. They assume access to reference data. So given that assumption, can we propose a baseline? And that's where we started from. So there are some, to further answer your question, I have a slide here. These are some examples of perhaps real world reference data availability. So there could be large publicly available data sets, for example. In this case, it's actually the opposite of what the existing methods are doing, because if you could train a method just using publicly available data that works well on your private data set, why would you even use the private data? So this is an example. There's also these business models where there could be the same data set coming from the same distribution, but one has more privacy than the other. And there's a few examples here.
So to kind of follow on, one of the things that's interesting that I did not get the intuition for is, can your approach help define that reference data set, like generate a better reference data set using some of the observations that you made in your work itself?
I wouldn't say that it can help generate a reference data set, but what it can do is, given there would be different relative training and reference data privacy settings. So given some of these examples, the reference data may be considered more private than the training data, less private. So if one were to have some reference data they would hope that the resulting model would protect the privacy according to that desired ratio. And what we showed is that our method has a very strong mapping between that, what you would want, and then what you result in.
Thank you.
I suggest we thank the speaker here, and if you have further questions, we will have a coffee break. Shall we thank you?
Thank you.
Our third speaker is a digital speaker. We have a video to watch.
Very much for joining me in this session, where I will present our paper, Systematization of Knowledge, Data Privacy in Virtual Reality. I give my thanks to my colleagues at UC Berkeley, Vivek and Don, and I have to read a disclaimer that the information and views set out in this article are those of the authors and do not necessarily reflect the official opinions of the institutions. In this talk, I will give you the context and our goal. I will give you the presentation of the different taxonomies on attributes, attacks, and defenses, and then other insights that I think you might find useful. It is a systematization of knowledge, so it's very hard to put everything on the presentation. So I encourage you to read the publication. The context. So virtual reality has gained momentum in recent years. A couple of years ago, Facebook rebranded itself from Facebook to Meta, as in the metaverse, which is intended to be a new medium for accessing the internet, and this access will be through virtual environments. And while that has been obscured by the hype on AI, the potential is latent, and other companies see how the future could evolve. And for example, Apple released their first ever virtual reality product. Now, privacy concerns are likely to be even more prevalent in the new Web3. So the Web2 concerns would still be in Web3, but because now you have new sensors, they are qualitatively different, then new privacy risks come, and then the attack surface increases. So there's already research showing that there is more personal information and sensitive, and it's observable. Luckily, there are also defenses against these attacks. And I here give you two definitions so that you know what I mean when I talk about virtual reality. In this context, it's a computer-simulated interactive environment experienced in the first person, and a state of privacy is a lack of a breach of any individual sensitive data attributes via identification and or profiling. So what is our goal? So we want to systematize knowledge on the landscape of VR privacy threats and countermeasures. And with this systematization, we taxonomize data attributes, protections, and adversaries in the literature. And we did all this by collecting and filtering 74 publications. So we hope that by focusing on highlighting the clear outstanding opportunities, we hope to motivate and guide further research into this increasingly important field. This is to get an overview of the context in which we are. So you have users that wear different devices, and the devices are registering the inputs from the human and also the environment. This data will be ingested by applications that request that data through APIs, and then they render the frames and different signals, and then they output that to the user. If you are in a multiplayer setting, you also need a server, and then you interact with other users. So there are attackers throughout this pipeline. You have the hardware itself, but you also have the client adversary, so the application developer, also the designer of the content that is within the application. Could be malicious. It could hide puzzles that reveal personal information without the user knowing. Then you have the server who gets the network telemetry, and then other users that may perform social engineering attacks. And the data fidelity and adversary capability decreases from left to right. There are different points where you can add protections. Here you see them at the different key points. And these protections cover privacy, security, and safety. And security and safety are covered in other literature. We focus mainly on privacy. So after collecting the 74 studies, we saw what the researchers were taking from from these devices and what they were inferring. So you have primary attributes that they measure directly, like body skeletal information, and then you can directly measure height. And then if you do some deterministic calculations, you can find other attributes, and we call them secondary, like your wingspan. Now you get the direct measures of your hands, and then you can calculate the wingspan of the user. And all this is used to infer identity, so to single out individuals amongst others, and also to do profiling, where you can perhaps gather data to infer age, gender, physical health, and so on. Here we cluster the different data in different classes. So you have your spatial and inertial telemetry, these are big ones. You have audio, text as well, video, physiological signals, which are very critical. And then you have system and network information, which is also prevalent in other systems. And then behavior. So even your avatar is releasing information about who you are, right? So that has to also be put into consideration. We took all the attacks from these papers and we classified them based on device, what attributes they use. You can see that most of them either do geospatial and inertial telemetry, or they focus on video or physiological signals. Then half do profiling and identification, and most of these attacks come from a client adversary. Some interesting stuff from these attacks is that the most accurate identification attacks rely only on the headset and handheld controller, so they only need position and acceleration. Profiling attacks that predict critically sensitive information, namely emotions, rely on health sensors. And once health sensors become more available to the public audience, the privacy concerns will be higher, and the countermeasures should already be in place. So there is plenty of work for researchers to do. There is a lot of these VR attacks are very invasive. Just look at the motions that they can gather from health sensors, or from like recording your face as well. And in terms of how easy these attacks are, social engineering attacks in virtuality are easy, and also these attacks that we gather are not rocket science. So servers and clients could perform them, and given that the standards of privacy are low in the ecosystem as of now, they might, as of today, get away with it. And the effectiveness of these attacks is high. So the most effective identification attack targets gait, so the way you walk, and they get 98% accuracy using only the inertial measurement unit. The identification, again, remember, is to single out one individual amongst many. And the most effective profiling attack infer gender, age, and ethnicity with close to 100% accuracy using variations of support vector machines and random forest classifiers. And the data was wide. So different aspects were gathered throughout the game, and it was a puzzle. And then based on the results of how they solved the puzzles, they would gain more information. We did the same for defenses. You can see that most of the defenses, unfortunately, focus on video, and they also protect the input to the device. The defenses can be classified in different types. So you have the perturbations, where they add noise, information abstraction. So instead of relaying the raw video data, they relay an abstraction. So just the shapes that build the table, for example. You have recognizers. So if you see if the device sees an individual in the background, they might obscure it. Analyzers, platform features, like for example, if you're in a virtual environment, only X persons can go into this area, and authentication mechanisms as well. And just to move to RQ4, which I think is the most important one to give the message, is that if a researcher does work on defenses, they should account for usability. Sometimes privacy comes at the cost of usability, and it should be accounted for when researching. We also mapped out all the privacy attacks to the most prevalent privacy attacks to the most suitable countermeasures, and we outlined the gaps in the research so that you can go ahead and produce them. we also saw that only 21% of the repositories were functionally operative, which is low. And also a quote from a study called Overseen said that 70% of the VR data flows from the most widely adopted VR device were not appropriately disclosed. So there's a lack of transparency in the ecosystem. This is what I meant before. And this should be tackled. Now, as the last thing is that based on all these research, we concluded on a few guidelines for an incognito mode for VR systems. First of all is that there should be a privacy-aware hardware design where if you leave the device, it will immediately stop recording sensing information. Your OS has to sandbox applications and it should monitor applications so that they don't behave in manners that are not were not thought to be. On-device processing, so if you can compute things locally is better from a privacy perspective. Browsing and communication protections, so end-to-end encryption, and also the incognito modes that exist today could be also brought here. You can add all the privacy enhancing technologies that have been discussed during the talk as well, and embed them at the application level, hardware level, and so on. And then the privacy settings for users have to be intuitive, transparent, without dark patterns, and the user data controls have to be there too. All right, this is the end of the presentation. Thank you very much.
I don't know if the speaker is online for questions. Yeah, then we can ask one or two questions. Do we have any? No questions? Maybe I can try to ask one question. Virtual reality, I think it will become very apparent for everyone, right? I'm imagining that there will be lenses integrated to our body, right? Where is the limit in terms of power consumption and privacy enhancing technologies embedded? Because there's a trade-off between power, utility, accuracy, and privacy. So can we win this fight?
Well, I'm hopeful that researchers come up with solutions like that. At the end of the paper, indeed, one of the kind of key findings is that not so many researchers that have researched defenses include utility metrics in the papers. And as you say, power is very important. So including these in all the papers that people do should be critical, as alongside other things like usability or gameability when you play, how deteriorated they are. And I'm sure as 5G progresses and cloud computing progresses, a lot of that could be offloaded. So then we'll have an easier time offering all these privacy and also usability features. But it's to be seen, and that's hence the call to arms to work more on defenses considering utility.
Yeah, it's I think multidisciplinary research to fight against these privacy issues in this context, virtual reality. Let's take the speaker again for this very beautiful soft paper. Now I would like to invite our fifth speaker. Anyone using VR? I see one professor, two. Anyone playing games or just playing games? Okay, two. Okay, cool. And the nice thing is we are perfectly on time. So whenever you're ready, you can start.
Okay, thanks. Hi, everyone. My name is Ferran Albert, and I'm here to talk to you about our work on computational differential privacy for encrypted databases supporting linear queries, which was a work done jointly with Sébastien Canard, Fabien Laguillomy, and So, the context we are studying here is a context where we have a database owner who wants to outsource their database in such a way that to a server in such a way that analysts can perform private data analysis onto this database without them having to own it. So the idea is that first this database owner will encrypt somehow this database and send it to a server. And then every time an analyst comes and wants to perform a query, there is some negotiation between this analyst and the database owner to be able to see if the queries can be asked or not, which will result in some token that then the analyst and the server can use independently to output this noisy statistic. This kind of situation can be useful when, for example, small companies that have databases that they want to put in online for some data analysis to be performed, but they may not have the infrastructure to house it locally, so they want to outsource it to a server that they may not potentially trust. So this situation has been studied twice before. First by Agarwal et al. In PETS2019, where they studied the case of histogram queries and they solved it using structured encryption. Then Bacchus et al. At CODASPI 2022, they studied the case of summation queries, and their solution was based on homomorphic encryption. The main issue with these two solutions is that they suppose that either the server or the analyst are malicious, but never the two at the same time. So what they do is that when they are considering privacy against a malicious server, they base themselves into the security of the encryption scheme, whilst analyzing the privacy against a malicious analyst, they use a statistical differential privacy. However, they do not study the case where there is a collusion between both. So in this case, what we propose is that what we need to analyze from a lens of differential privacy is not only the noisy statistic, but also the encrypted database and the token that the analyst has received from the database owner. So as building blocks to fulfill the diagram we had at the beginning, one immediately can think of, okay, we can combine differential privacy with functional encryption. As most of you here will know, differential privacy is a property of randomized private mechanisms, which at a high level verifies that the probability distribution of the output of this private mechanism applied to two neighboring databases is really close in a statistical sense. The important thing to remember here is that this is a statistical property. On the other hand, functional encryption is a generalization of public key encryption, where there is here we are representing secret key functional encryption. There's also a public key variant, but we're interested in the secret key one, where the idea is that there is Alice who has a master secret key, and they can encrypt ciphertext and then send it to Bob. And then each time Bob wants to obtain a function applied to the message, they send this function to Alice, who will create, using the master secret key, a functional decryption key, which then can be used by Bob to obtain, using this functional decryption key and the ciphertext, the function applied to the message. The other important thing is that this standard functional encryption only outputs deterministic output. So combining it naively will not work, since on the one hand, differential privacy inherently will use noisy output. So we will need to use a randomized functional encryption by Goyal et al., which essentially the overview is the same, but the output is a randomized function, a probabilistic function instead of a deterministic one. On the other side, the security of computation of functional encryption can only be proven under computational assumptions. So studying the differential privacy of the ciphertext can no longer be under a statistical point, so we need to use computational differential privacy. Adding these two together, we do obtain that if we have a randomized functional encryption whose output is computational differential private, that holds simulation security, then the whole mechanism containing the output, the ciphertext, and the functional key holds computational differential privacy. So the next question is how do we actually instantiate some randomized functional encryption? It does exist functional encryption for generic circuits, and there is generic transformation from deterministic functional encryption to randomized functional encryption. However, functional encryption for generic circuits requires really strong assumptions like indistinguishability, obfuscation, or multilinear maps. And the standard transformation from deterministic functional encryption to randomized functional encryption requires extra assumptions like non-interactive zero-knowledge arguments, PRFs, or one-way permutations. So to improve the efficiency of the scheme, the one thing we can do is restrain ourselves to a more contained class of functions for which we know there is efficient constructions. This can be inner product functional encryption, which is functional encryption for linear queries. And a first naive way we can think of adding some noise to this inner product functional encryption would be to use function hiding inner product functional encryption, where it is equivalent as the ciphertext protects the message, the functional key will protect the function. So by embedding the noise directly in the functional key, there is no issue of leaking the noise. However, function hiding inner product functional encryption requires pairings, which are computationally not the best in efficiency, and also will require heavy functional keys, because essentially what we are doing is encrypting the function. So what we propose is by using techniques of multi-input functional encryption, where the idea of multi-input functional encryption is that one can encrypt the message during different independent times. So the idea is that during the encryption of our randomized functional encryption scheme, we use one input to encrypt the message. And during the key generation of the randomized functional encryption scheme, we encrypt the noise. So we do not need extra assumptions. So what we obtain is this result that if we have an inner product functional encryption scheme, which is simulation secure, then we can construct a randomized inner product functional encryption scheme that is also simulation secure for one database without extra assumptions. And on top of not having any extra assumptions, the overcost in regards to the base inner product functional encryption scheme is very low. There is no overcost for the ciphertext, and the overcost for the master secret key and each of the functional keys does not depend on the size of the database. It is constant. So adding all this together, what we do is we instantiate what we call private functional encryption, which at a very high level overview, what we do is using our randomized functional encryption, the database owner will encrypt the database using the randomized functional encryption and send it to the server. And then every time they receive a linear query Y, they will use the key generation algorithm to get a token, which then can be used through by the analyst and the server to obtain the linear query plus some differential private noise. We have also implemented this scheme, which is has the badge of artifact available. Interesting here is we can see effectively that there is no dependence on the database size for the master secret key and the functional keys. And on top of that, we keep a linear relation. The computation times grow linearly with the size of the database, which is expected since inner product functional encryption does increase linearly with the size of the input. And thank you very much for your attention, and I'm open to questions.
Okay, any questions? Please go ahead. Microphone is coming.
Yeah, sure.
Sebastian Hasler from the University of Stuttgart. Here you use randomized functional encryption. So the output can be randomized. What does this depend on the secret key, or for a fixed secret key, would you get a fixed output, or is the output still randomized after after the analyst gets the secret key?
What we wanted was to avoid repetition attacks. So what we have is that one same functional key applied to one same ciphertext will give the same output.
Okay, yeah, that's,
but different functional keys will give independent output. Like the randomized will be independent. The randomness will be independent for each functional decryption.
Okay, thank you. Yeah, that's why I asked, because otherwise, if the analyst and the server would collude, they could repeat this again and then get many outputs.
I have a question. You mentioned that the query can be only linear, right?
For this case, yeah. The thing is about functional encryption that it is a really recent primitive. So efficient schemes are for concrete functionalities. There are not as many. We have some for linear queries, and we have some for quadratic queries also, which we have as a follow-up work we have already adapted for differential privacy.
Nice, very good. Any other question? No? Then let's give a big hand to the speaker. Thank you very much. And the last speaker of this session. Okay, it works. Okay, I think it's good. We are good to go.
Okay, so I'm really sorry if this talk may seem like the last talk, because obviously we had the same idea. So I'm going to present our research on differential private functional encryption, and I'm Jasmin Salonis, and it's a joint work with Frederik Armknecht and Linda Schreihaft. Okay, so as many of you and also the group before us, we are interested in realizing privacy-preserving analysis, and just from a really, really high-level view, we have on the one hand various users which have all sensitive data in some form, and on the other hand we have an analyst that wants to evaluate some function on this data, and of course we have some sort of computational process. And in the classical medical context, for example, the analyst holds all the data and can do anything. And of course, this is not privacy preserving. And we know today that not only the input data is sensitive, but also the outcome can reveal too much information about the data. And we also know how to solve this by introducing differential privacy. And I think we all have heard enough about differential privacy, so I'm not going into detail here. And we also know that the input data is sensitive and that we can use cryptographic mechanism to provide input privacy. And there are a lot of solutions that are based on multi-party computation or homomorphic encryption, but we wanted to investigate another primitive that is rather new, and it's functional encryption. So again, just a quick overview about functional encryption. We have our data from our different users. We have an authority and we have our analyst, and the authority provides individual encryption keys. So in the multi-input context, each user gets an individual key. the user can now encrypt their data and send them to some data holder that may be the analyst. And the analyst can now request functions and gets decryption keys for associated with this function. And we believe that this setup most closely reflects the current situation, more detailed the situation of differential privacy. And our question was, how can we use it for privacy preserving analysis? And basically, how can we encode the noise, the randomness for differential privacy? So we present the new primitive that we call noisy multi-input function encryption or differentially private function encryption. And here in the key generation process, noise is sampled according to a distribution D that is associated with the function F. And so the analyst who decrypts the data or who evaluates the decryption key on the ciphertext now evaluates not to the function f of x, but f of x plus some noise that is sampled via the distribution that is associated with f. And so this can directly be used for privacy preserving analysis. And there are some open questions that we solved in our paper. So first, when is the noisy output correct? How can we ensure that an attacker does not learn too much information when the outputs are noisy? And of course, how can we construct schemes? So for the first question of correctness, at first, the correctness definition for MIFE is rather straightforward. So the decryption on the decryption key and the multiple ciphertext should be f of the message, so the plain text. And for noisy multi-input function encryption, since we embed a distribution in the key generation process, we also need to deal with probabilities in our correctness definition. So we say a noisy MIFE scheme is correct if the probability that our decryption algorithm evaluates to the function plus the sampled noise is the same as the probability that this noise was sampled via the given distribution. For our next question, which is basically the security definition, we again will look at the standard security definition of a multi-input function encryption scheme. So it is a classical indistinguishability game. The attacker can adaptively make any queries of messages and also decryption keys. And so he queries some messages x0 and x1 for the slots and gets ciphertext, and he also can query functions F. And in the normal setting for multi-input function encryption, if we only have message hiding, he only can request one function. So F0 and F1 are the same. And if we have function hiding security, which was also in the last talk, the attacker can request two functions, so for each case one. And we have in function encryption a special requirement that the evaluation of the function on the messages for each case needs to be the same. And this may seem rather restrictive, but simply means that the attacker cannot distinguish between the cases simply by evaluating his decryption keys on the ciphertext. So we have on the one hand message hiding, where we only hide the message in ciphertext, and on the other hand we have function hiding, where we also hide the function and the decryption keys. And what we basically want is only noise, some form of noise hiding, because we do not care if the analyst knows his own function, but we care if he knows the noise or not. And so the next contribution was to adapt a security definition for noisy multi-input function encryption. And it's almost the same as for multi-input function encryption, but now for the decryption key query, he cannot request two functions, but rather one function together with two noise values. And in the key generation process, the function is associated with the distribution that outputs one of these values with 100%. So the attacker has maximal power over the noise, and the challenger then provides the decryption key that that decrypts to f of x plus the noise beta. And if the analyst cannot distinguish between these two cases, then he has also no additional information. So again, we have our restriction that the function f evaluated on our cipher or our plain text plus the noise should be the same for both cases. And so we show that noise hiding is only more relaxed security definition where only part of the function is hidden, so only the noise is hidden. And this leads us to our next question, how can we construct such schemes? So we already heard one scheme, but we also present a general transformation in our paper. If we have a function hiding MIFA scheme, then we can build a secure, noisy MIFA scheme. And this is basically what we saw before. So we take the same setup, encryption and decryption algorithm, but for the key generation algorithm, the authority first samples some value over the distribution and sets our function f star as f plus the sampled value, and then requests a key from our MIFA scheme for f star. And of course, f star needs to be supported from our MIFA scheme. And we show in our paper that if S correct, then also our noisy MIFA scheme S star is correct. And if S is a function hiding MIFA scheme, then S star is a secure noisy MIFA scheme. And we also present two schemes in our paper. So the first one we called noisy dot. It's a noisy MIFA scheme for inner product functionality that is built from the general transformation from a function hiding MIFA scheme. And the other one is diffpipe, which is a noisy MIFA scheme also for inner product functionality that we built directly, which has only single message security. And both of the schemes are based on linear groups. We also did some implementation and have some results that are not that fast as in the presentation before, but we did counting queries evaluation on real medical data sets, and one of these data sets was the NANUS 3 data set, which has roughly 16,000 records with each 12 attributes. And so noisy dot needs around 10 minutes to evaluate and diffpipe only 6 minutes. And this shows that the relaxation of our security notion to only noise hiding provides for new and more efficient schemes. So thank you very much. Are there any questions?
Yes, do we have any questions? Please go ahead. I can give the mic.
Yeah, so I wanted to ask about the introduction of the new primitive. So the decryption is the addition of the noise and the f of x.
So you mean
here?
Here, yeah.
Would it make sense? I'm just asking, like to have a. So this is a very specific relation between the noise and the f of the inputs. Would a generalization make sense? Like the decryption is a generic function, or capture other function rather than addition of the vector, or the fact that we add over arbitrary distributions is generic enough?
So we use differential privacy as the basic idea, and I'm not sure if I understand your question correctly.
Yeah, it was very clear. So let me repeat. So what I'm saying is, like, it just has to do with the definition of the primitive. Okay. Like the decryption is f of the inputs plus the noise.
Yes.
So the operation of addition is quite specific on how f of x and the noise are related in the decryption output. Would a generalization of the primitive make sense, and would it capture other schemes or constructions that are interesting? Or just staying at this level is generic now?
It's a good question, and I'm not sure about. We did the addition because it's a standard mechanism for differential privacy to add some noise, but it's worth investigating more, I think.
Thank you.
Why do you think that the computational difference is there between yours and the previous talk? It's significant. They were using pairings?
No, they didn't use pairings.
I thought it was pairings. Do we have this? Yeah? No?
No.
Okay. So what is the difference coming from?
I think the difference is because you use only a set P addition. So we use bilinear groups and you do not use bilinear groups. And I think this is the difference.
Okay, interesting. Any other question from the audience? If not, I want to compliment all the speakers. They were perfectly on time. Very flawless session with 6 amazing speakers. So let's give them a big hand. And I guess at 5 o'clock we have the town hall meeting, right? See you there.